just gotta use my hands. They're so good, these guys are. Yeah, nice. Get the clock on too once we start, just so we don't go over. Nice.
All right. Good morning, everyone, and thank you for joining us at this morning's JuliaCon session. Please join me in welcoming Michelle Pounds and Spencer Clements from the Utah State University Analytics Solutions Center, and they will be talking about Bruno.jl, financial derivative asset pricing and modeling.
Thank you. Everyone hear me good? So thank you for coming to Bruno.jl. If you want, you can get our docs right there, that QR code. It is for version 1.0. Over the last couple of weeks, we've been working on 2.0, and all the code snippets and graphs and documents and assets, whatever, will be based off of 2.0, which will be coming in the following week or so, give or take. So today we're going to talk about why we chose Julia for this project, and how the Julia language really shaped the design and patterns that we used inside of Bruno.jl, and why multiple dispatch is so effective, and including just the different things that Bruno.jl is really good at doing. So at the top, I'd like to thank our mentors at the Utah State University Analytics Solutions Center. Without their help and knowledge, we wouldn't be here today. They were really our guiding star and invaluable knowledge and just support and all the good different things. So why Julia? So back when we first started working on Bruno.jl, we were contracted by a company to create a simulation environment that was flexible enough to really do anything they wanted to do. They knew they wanted to do some form of derivative pricing, a little bit of just general asset pricing, but didn't know exactly which direction they wanted to go. So they originally built us just to make a very generic simulation environment. And as you do, you start the conversation of, well, what languages do we know? What do we think would work well? And the usual candidates came up like Python and Rust and C++, and someone actually recommended Fortran, interestingly enough. But each language had their own reason, like to ignore, like Python was just too slow. We needed to be able to just be blazing fast, and Python was too slow with its very tightly coupled inheritance system. Rust, the problem with Rust was that it just wasn't verbose and expressive enough, where I love Rust and it's great for multi-threading, but just having someone pick up the package and use it wasn't exactly plausible with Rust. And we skipped over Fortran because it's Fortran. But one of our mentors, Tyler Bruff, recommended that we go watch a video called The Crazy Effectiveness of Multiple Dispatch by Stefan Krupinski back in the JuliaCon 2019. And in the video, he talks about all the things we're really looking for. We really wanted to have a programming language that was blazing fast, something that was very flexible and was easy to read and learn, where if you knew Python, you're going to pick up Julia really quickly. So what is Bruno.jl? A lot of people come up to ask us, like, well, why would I use this package? What secret sauce does this package give me to beat the market? And, well, my answer is it doesn't give you the secret sauce. If we had that, we would be out right now trading and making lots and lots of money. But instead, Bruno.jl gives you the ability to develop very quickly the different ecosystems that you need to test your theories.
So Bruno.jl, it does 4 different things. The first thing it has is it has a descriptive type system that mirrors the real world. So for example, if you have a derivatives contract, well, it's going to reference some underlying asset like a stock. And that's the exact same way that the type system works in Julia. So in this way, if you are a finance professional or just like a day trader wanting to try and use Bruno, you can have your type system set up similar to how your actual portfolio is set up. And then the second thing it can do, it can generate a simulated time series using parametric and non-parametric models. So for example, here's 2 different simulated stock paths based on the left, we have a parametric model. On the right, we have a non-parametric model. So this just generates these time series that we can use in other parts of the package. It can price assets, different types of assets using different types of pricing models. So for example, if you have a European call option, you can price it using several different models for like the Black-Scholes, which is really common, or different Monte Carlo methods, or binomial tree, etc. And then the last, we think the most important part is that it gives you this simulation environment. So if you come to the table with some sort of an algorithm or an idea of, hey, I think that this is going to make me money, then you can try it out. So we like to say that Bruno is like backtesting on steroids, right? We specifically wanted to make Bruno, modular enough and extensible enough so that, let's say you wanted to just backtest and you pull prices from Yahoo Finance or Alpaca or whatever for the past year, you can try out your strategy on that and see how much you would have made. That's pretty standard for many backtesting packages. We also wanted to include functionality to not only do that, but do it for derivatives, which derivatives are difficult because of the time to maturity issue. Instead of having just one dimension of prices, you're going to have 2. We also wanted to be able to do that using different pricing methods for the derivatives and to be able to use different models. So if you wanted to use real data, you can, or if you wanted to switch out the real data and use some of these generated time series, like for example, if you wanted to use geometric Brownian motion or something else to try and project into the future, you could. So that was the guiding principle, is we wanted to find a way to be able to have these different modular abilities and be able to pull one out and put another one in and be able to have the package still run. Now, how we did that was using multiple dispatch. So multiple dispatch in Julia was key to even having the package work. As you can see here, our price method has 16 different methods in it. And what that means is that for every different option or every different asset that you have that you could price, you also pair that and dispatch not only based off of the type of asset, but off of the pricing method. So for example, if you wanted to price a European call option versus an American call option using some pricing model, that they're going to work differently. They're going to use different underlying math. They're going to do something. And so you can just use the one price method, put in both of those, and it will automatically dispatch to find the correct underlying math to use. This also helps because, in fact, we had a conversation just before this about, hey, have you implemented this or this? It's really hard for just anybody to implement a full range of all the different type of pricing models, right? There has to be hundreds of papers out there of different ways to price these call options or forwards, futures, whatever it may be. So instead of having to have all of those be explicitly written inside of Bruno, if a user wants to come to the table with a different type of pricing method, all they have to do is extend this price function with their new functionality with new types. So it makes it so that if you want to use the built-ins in Bruno, that's great. But if you also want to overload it with your own ideas later, great. We wanted this to be as flexible as possible going forward. The other thing that this allowed us to do was inside of our simulation environment, instead of having to try and make a lot of different functions and have case statements with like 15 different cases or whatever, we're able to have this price be called inside of our simulation environment. So if you want to know the price at any given time in your simulation of a given asset, you just call price and we'll give it to you regardless. And so in that way, we could keep the code base much simpler and much smaller, allowing the compiler to optimize as it could and find the right dispatch method. So here's just a couple code examples where you can see we're dispatching off of the type of asset as well as the type of model that we're using. We have several of those. But this helps us this helps development speed not only for us, maintainers, and us, I mean royal us of everyone in this room, please, pull requests are welcome. But the maintainers of Bruno, it's not only helpful for us because we can just extend this with more and more functions, it's helpful for users as well. As I said, they can extend the functions. But not only this, a user does not have to memorize or look up or use documentation for a bunch of different function calls. You don't have to say Black-Scholes method price this thing and it will do it. The user really only has to know 3 functions. There's a pricing function, there is the simulating function, and there's a time series generation function. And that's really it, unless you want to get into the deep nitty-gritties of the package. You can use it with 3 different functions and with some constructors to get into those. This way, if you are new to Julia, as a fair amount of the finance community is, or if you just want to write simpler code, you don't want to worry about all the boilerplate, that's handled by Bruno. So the part that we're most excited about is the simulation environment. So the reason the simulation environment is so important to finance professionals comes because of this. Now this is 2 different implementations of a hedging strategy. It's a fairly simple one, been around for like a long time at this point. This is a Black-Scholes delta hedging strategy. So really well known, really famous in the finance community. To be able, and I know this because we tried this when we first started writing stuff in Julia, to write a simulation environment in Python is very much a minimum of 100 lines of code, because you need to be tracking all of your variables through the entire simulation. You need to be tracking how much you own of different things, what is the prices of the different things. You need to be accruing interest over the different time periods. Whereas in Bruno, we can handle all of this ourselves, and the user can really just focus on that algorithm, which in this case, the algorithm is very simple. We just have a variable delta, which it's called a Greek. It's just a math equation based on the option. And we buy and sell to get up so that our stock holdings is the same as that delta. So going from 100 lines of code in Python to this. This is the entirety of that trading strategy to be able to use it, and it works. So in this way, we go from having to develop a new simulating environment every single time to being able to use something really fast and get your ideas. So if you have an idea, let's say that you have an algorithm you think is going to work. Like let's say that you're going to buy on Monday and sell on Friday, because I'm sure that's what all the hedge funds are doing right now. As long as you can express that strategy in an algorithm, you have to write down just the algorithm, throw it into Bruno, and Bruno will handle everything else. It will handle all of your variables. It will handle accruing interest. It will handle time steps. And it will give you back that data at a very granular level.
So then we move into our code a little bit to give you an example of what we got going on. Next one, yeah. So here we have an example of just a very simple, does this work? So what we're doing here is creating a price array from $1 all the way up to $257, just a linear, every day, stock price goes up by $1. And our strategy is, on the very first day, we're going to buy, and on the very last day, we're going to sell. So hopefully we make money, which I think we should. And this is what our holdings look like throughout time. Because the stock is going up by $1 every day, and we own 1 stock, our portfolio is worth $1 extra every day. And our cash reserve actually goes down this first day when we buy $1, and then at the very end, we sell for 250 something, and we make a bunch of money. The power of Bruno 2 is, as Mitch said, you don't have to track all these different variables, where we track the interest rate, we track how much cash you have, we track how much you owe, just all the different variables that you might be interested in, we track a fair, healthy amount of them. For example, of something a little bit more intense, something that someone might actually do, we load up Apple prices and do a mean reversion strategy on it. This is what the Apple prices looked like for the last year, and this is what the algorithm did. So in the first little bit, we bought around day 49, lost a lot of money because we had to borrow it, but our portfolio is slowly going up as the Apple stock also goes up.
Awesome. So moving forward with Bruno, what we want to go into later is we want to really optimize this and be able to make it even easier for the user. So the first thing we want to do going forward is all of our data generation for those time series. Right now, it just returns a big old matrix, and you have to iterate over the matrix yourself, which it works, but we want to use the iterator implementation in Julia so that we can have these be generator functions, and you can just say for data in and give this iterator object, this generator object, and it will give you that generated data. So that's one of the next things we want to do, and that can be optimized so that it's a lot more memory efficient other than just giving you a big fat matrix that you can have fun with. And then we want to have a dedicated Monte Carlo simulation environment. So if you think about those graphs that I showed you before with the profit and loss distributions, those were all handled. So Bruno will do the individual simulations as of right now. It will do at each point. We want to extend that so it will also say, hey, do this 1,000 times, give me back my distribution. So right now the user has to do that. User has to build a for loop and has to rebuild that simulation environment at every step. So we want to build one inside of Bruno that handles that. And since each run of the Monte Carlo simulation will be independent, then that can be parallelized. We can use multi-threading and really squeeze out as much performance as we can from Bruno.
Something else that we forgot to put on the slides, as we're going through and doing these just different environment simulations and really making it as verbose and really thoroughly tested, we keep finding new things where we're like, oh, this would be really cool, this would be really cool. So we're also planning on adding just a lot more of the pricing options. Eventually we're going to add bonds and swaps. And right now we have commodities, but we don't really implement them at all. So, yeah. Do we want to do code or anything, or we could move on? I'm good. So we blazed through this quicker than we thought. Any questions? Yeah.
I saw you had delta hedging up there. Do you also have the options for other Greeks?
So the way that we're implementing right now is the package doesn't calculate the Greeks for you, unfortunately. We could in the future. So the way the simulation environment works right now is you initialize, in fact, can you go back to simulation environment? All right, right here. So if you look down on, yeah, so here I can. If you look down in this bottom portion where it says simulation environment, so that is creating just an empty one. And as soon as you have this empty simulation environment, you have to add anything that you want to use in said simulation environment. So if you want to use an Apple stock in there, you have to add the asset. And as soon as you add an asset to the simulation environment, then it will load in all the prices and it will automatically calculate the moving window average of the volatility for that stock. But then you can also add in certain variables. And so those variables will be at each time step throughout the simulation. So like let's say that a really simple example is, I don't know, you need to know a single price point inside the simulation. It will load that single price point in and refer to it at each point in the simulation. But if you have a variable that changes throughout, so like your Greeks, so if you wanted to do delta, if you want to do gamma, rho, any of your Greeks, then you could calculate them, put them in as a variable, and you'll be able to trade off of that variable inside the simulation environment.
And to add on to that, you can also add other stock values. So if you wanted to do like a pairs trading, you could add multiple stock values. If you had some variable called foo that needed in your super specials trading strategy, you can add that as well. You're not limited to what we thought you would need. It's very extensible, and if you want it, you can get it.
And you can access any of those variables inside the system. So like if you want fun fact, you can access all of the future price points as well as if you really cared. So if you want to be a fortune teller, you can do that in Bruno, but I mean, that would be a little silly.
And for example, I access the stock prices going back 5 days right there for the moving average, just as a super easy example.
So, are there any other questions?
That's a trading strategy where a portfolio is built out of hedged pairs. For example, I'm long stock, I'm short spikers, and let's say that hedging coefficient has to change every day. Is that something? How would you construct that?
So your hedging coefficient, what is it depended on? Fair enough. Let's say that it's some function x. So inside Bruno, you can have inside the add variable functionality, then one of them you can add a single price point, it'll add that. You can add in a vector, and it'll add that. But you can also input a function, and you can have the function refer to stock prices inside of the environment. In fact, it allows for Julia's nice do end block as well. So you can input an anonymous function in there. So if you wanted to input in your proprietary function to give your coefficients, it would. And then you would just have to use so inside, let's go back to this one. So inside of any strategy, the first thing you need is, on that first line after the function, is environment setup. That defines inside of your strategy, it gives some nice function closures that we've made that call a underlying buy and sell function. The underlying buy and sell function just handles all of the how much do I have at this point, how much money do I pay or get from said buy thing, and etc. And so all you would have to do is, as soon as you have your coefficients loaded in as variables, then you just say buy this much of this stock, short this much of this stock, or sell. Selling, you're shorting, you have negative of it, up until your coefficient, and you run the strategy.
Commission on spread.
So as of, and it's funny, in version 1.0, it's in there as a keyword argument that you can have. Version 2.0, that's the reason it's not released right now, is because we still need to add that. But it is, so inside of your, inside of that buy closure, so right here where it says buy Apple, and then that number is the amount that you want to buy, you could also have a keyword argument saying your transactions cost, and it will add that, it will subtract it from your cash holdings.
I have a question about getting filled. So, if I'm buying Apple, there's a bid, there's an ask price in real life, right? So how do you capture the friction in the market and guarantee that you're going to get, filled at a particular price?
That is a really good question. Right now, we don't do bid offer spreads. We should, which that's a lot more complex. Right now, you can only have a single price point, and that's both your buy and your sell. So you're assuming like a zero. The reason behind that is because this was first built for academics, and then we're like, oh, hey, by the way, hedge funds might want to use this someday. And a lot of academics assume no arbitrage conditions, and so you have your ask and your bid are the same. So that is something we want to implement eventually.
And we could probably implement that fairly easily in the buy and sell conditions, where you just add the functionality when you try to go to buy or sell, the friction. So I don't think it'd be too difficult to do, but again.
Do you have different kind of order types? So limit orders versus market orders?
So right now we do not. We assume that you're able to execute your order at any point. You can do that yourself. You can define a limit order as like an if the price gets to this point, then buy. And that's effectively a limit order functionality. There are other packages that do similar things. If you want, I can talk afterwards of some other packages that do offer different types of order types. However, as of right now, they haven't implemented derivatives into their functionalities.
Any other questions?
Current users of your package, or what's your target?
So our current users, we had one person use our package to help write their thesis for their doctorates. And then we had that company that I mentioned at the very top. They ended up using this for a little bit to do what they needed to do. Can't really talk about what they did because NDAs and all that, but
They extended the functionality.
yeah.
So they had a very unusual type of option. It was dependent on something that was not tradable. And so they were able to implement a similar thing by extending the functionality of Bruno on their own ecosystem. Yeah.
And I also use it to trade stocks right now. So I use it to backtest. So, yeah. But our main target audience would be just people like us who are interested in playing around with the financial markets, market makers, and researchers. Something I wanted to talk about is a lot of the researchers in the finance field, economics field, they know programming, but they don't want to sit down and program all day. They want to do their research. And that's the beauty of this, is you can write, 10 lines of code and be able to do something that would usually take you 200-300 lines of code. So.
In the real world, the financial instrument is 100,000 times more complex.
Oh, exactly.
Yeah, that's what I'm thinking. Are you guys planning to make it bigger to become like open source, like pricing model, like maybe for a small hedge fund in the future they can use it?
If some hedge fund wants to hint come fund me, then yeah, I would extend functionality for them as long as they would want. But right now it is more of a for researchers or for researchers or people that don't need that granularity of the complexity. If you're looking and a price is a price to you, you don't need to know the volume, you don't need to know that kind of stuff, then this would work great for you.
Good, awesome. Thank you guys.
I can hold one. I can hold one. I can hold one.
Yeah, sure. Okay. Let's go to switch on. It's on. Okay.
Detecting when the market conditions are violating the assumptions of the model.
All right, we're going to be starting with our next session really soon. So may I just request everybody to, get a chair, get comfortable. All right, our next speaker is Aaron Wheeler. He's a PhD student at Cornell University, and he's going to be talking about introducing a financial simulation ecosystem in Julia.
This thing on? Okay, so first off, thank you all for coming. Thank you to JuliaCon for giving me the opportunity to speak. What I'm going to talk about today are two packages in particular that make up a different kind of financial simulation, right? So this is going to be a baseline implementation of an agent-based financial simulation. What I've been working on as part of my PhD thesis, right? Packages are listed there. So typically when people think of like financial modeling, they'll think of two different approaches, like we can say market replay or these top-down forecasting methods, right? So both of these will rely on historical data sets, which can be expensive, finite, and static in the sense that, it is what it is, what happened, right? So with backtesting, right, we're going to wind back the clock, and we could send in a model just to see how it would have performed if it would have been there at that, point in time. And so these can be quite sophisticated and, work quite well. One thing which can maybe be a downside is that they're unresponsive. So if you, there's no reaction to your action. That feedback is not present in something which is only using historical data sets. There's no divergence from price history. And moving on to forecasting, these top-down methods, have been around for a long time. Can be like very famous, and they'll essentially condense these very complicated things like price series into a small amount of parameters, which we can then fit to historical data and then use to generate these synthetic time series. And one thing that these can struggle to do sometimes is model these financial contagion effects. So effects in like a big network of things and how maybe things can interplay there, or emergent phenomena. So things that can manifest unexpectedly, things like the flash crash of other market crashes. Ideally, we would want something that maybe can sort of abstract this idea of time here and capture the statistical properties of these financial time series. And rather than maybe here try to focus on prediction, I want to focus on representing these financial time series as best we can, so that we can then turn around and go and interact with something. So having a feedback effect for the actions taken in this simulated environment. We want to be able to tune it so we can generate data for things that we don't, either we have only rare instances of in history, or maybe for things that we don't have any examples of in historical data. And so the ability to generate these what-if scenarios. So let's say if we wanted to generate 1,000 different market crashes, and then maybe see if we can train something, an algorithm to be robust against that. Or if I'm a policymaker and I want to change some sort of market rule and I want to generate data for what the effects of that could be at the aggregate, right? We want something that's expressive, something that can generate these really complicated and nonlinear effects that we do observe in these really emergent properties, right? So this is the vision. This is not yet the reality. What I'm going to talk about today is our progress toward this goal, how Julia fits into that, some preliminary results, and then some next steps. A little background. So real markets operate through order books. They can be thought of as this representation of supply and demand, two-sided. Buyers submit bids, sellers submit asks. The bid price is the highest price a buyer is willing to pay. Ask price, the lowest price a seller is willing to give up their asset for. And if you're patient, submit your bid here in this queue and then wait for things to sort of shift your way through a limit order, right? This sort of pending order in the queue. If you're impatient, you can go and just immediately execute this. So seller goes and acquires things at the bid price, buyer similarly at the ask. And all of this will occur at a snapshot in time. And then as this evolves, we get these several various states, and the price emerges from this. And this is what we model. We modeled the interactions at the micro scale. So the actions behind the orders, they're being submitted here in the book. And we're almost hoping that these, the properties we really care about, like the price, et cetera, just emerge as a byproduct at the macro scale. To do so, we use agent-based modeling. So this has 3 separate components, the first being software agents. These are autonomous agents that are heterogeneous, right? They can be defined with different properties and exhibit fundamentally different behaviors. The interaction includes the available actions made to these agents, as well as the explicit structure to which they are linked. The environment defines the state of the system. This includes the observation space, observable variables, things like external shocks to the system, things that can be like news propagation, right? And a little more nuance can be the representation of time. Do we look at time as a discrete sort of trading round where you can see everything that happened before it gets to your turn? Or do we think of this more as how it is in reality, where it's continuous and decisions are being made in parallel? 2 additional steps to generate realistic phenomena. We rely on both calibration and validation procedures. Calibration occurs before running the model. It's where we sort of determine these parameters to then get these models to generate realistic phenomena. These can be calibrated through heuristic methods, or if you've got it, historical data. After you've run this model, to then trust these results and make sure that this is something you can depend on, we can run a series of tests. In the literature, this is known as stylized facts. They're essentially these statistical regularities that have occurred, and they've been studied for a long time, really a subject in and of themselves. And we'll look at these as like a test set and say, okay, if we can achieve all of these, then we can now have like this sort of abstract, generalized, fidelity test, right? So we're able to then, guarantee that, or I shouldn't say guarantee, but able to have more trust in our sort of what-if scenario where there's no ground truth. We can say, okay, well, there is some sort of built-in trust that we can have here through this validation procedure. How we implement this in the Julia leverages several existing packages. Our 2 main ones are that we're going to talk about here are these trading agents. These are the actual agents who will be making these decisions. And the Brokerage.jl is the sort of how we've implemented this as like a server that is going to process all these orders. The agents make decisions in parallel. The orders are processed serially. Within Brokerage.jl, how this is implemented right now is we'll spin up a remote server using http.jl. It's going to route these internally to these various different microservices. There's this API interface that the agents will then connect to, right? And then these orders will be routed to their respective location. Could be a relational database so that we can have a large number of agents, or they can be processed through these order books. We've implemented in-house a package that essentially reproduces these matching algorithms. It's been validated against empirical data, et cetera. And then they'll also query things like the observable market information. So the agents themselves, we're going to sort of take a minimal assumption approach here, right? Because it's a baseline. We're going to think of the first type as these liquidity providers. So these are going to draw randomly a limit price, this normal distribution, depending on the market state as well as their agent state, as aka their inventory and cash. They're going to take an action and add these orders to this level of the book. They're going to be the primary source of price movement resistance. Liquidity takers similarly will determine a random amount of their wealth to put up to risk and then randomly set these portfolio weights. Similarly, they'll take price away. They're the primary movers of price movement. They only do market orders. Liquidity providers only submit limit orders. A little more specific is the market makers. So they're going to determine a random spot within this sort of price levels to submit this limit order and concurrently place them. If they have an inventory, sometimes they'll also hedge. Also, all of this is done randomly. We did design one intelligent agent. We read in the literature that just using these sort of simple zero intelligence, they call them behaviors, a lot of times you'll observe like price instability. And so this is added just for the sake of wanting to have less unrealistically volatile behaviors, and we're able to see that just by introducing this intelligent agent. This agent uses these handcrafted optimization procedures. I just used JP Morgan AI research. They had some sort of a implementation. We made our own version of that with online machine learning, so it could function on the fly. And essentially how they work is a 3-step decision policy. This is implemented through convex.jl for the optimization procedures, which I could make convex, and then jump for the optimization procedures, which I could not. And so this simulation can run without the intelligent agent, but we do have it there for the sake of completeness and stability. So how this will work is, as an example, we'll spin up a server, initialize these agent parameters, and then generate this price and volume data. And then over time, we're going to notice these actions come together and generate these macroscopic properties at the aggregate. So in line with wanting to make minimal assumptions on these initial agent behaviors, there's minimal parameters. We're going to look at the number of agents, instantiate their cache and inventory range. They'll be allotted something within here, and once again, randomly, and then they'll have a trading frequency. And then as for the market, we just set the market hours, number of assets, etc. In terms of performance, we've been able to scale this up just because of the fact that everything is distributed, right? And so as the first sort of a proof of concept, we started with just one asset, 142 agents, moved on to something which these parameters were derived a little bit from. They're loosely based on some studies in the high frequency literature. And then we've just scaled it up to 30 assets and over 100,000 agents. All this was done with very modest research equipment, my desktop in the office, right? And then when my lab mate wasn't there, his desktop in the office, right? And so, I think with minimal optimization in terms of like getting, I do what I can, right? But I'm sure that this could, perform a lot more with more time and effort. So let's talk about the validation. These stylized facts. So all these facts will run across 10 different trials of this synthetic price series, and all the results are consistent across these 10 trials. A lot of these stylized facts will take as an input a return series. Returns we can just think of maybe as normalizing the data in a sense, and pretty simple, right? Just return of investment, the gains and losses investment generates over a period of time. The first one I want to look at is the non-Gaussian characteristic of returns distribution. This matters because extreme events occur more often than one would normally expect. And this is first mentioned in the literature some time ago. I've re-implemented this with some recent data, just to ensure that it's still there, as well as our tests are working as they should and not wanting to get any false positives. I've included as a comparison maybe something we've gotten from a traditional model, something like geometric Brownian motion, which is then fitted to the Apple data in the top right, and then what our simulation would get when it's removed from any sort of empirical data. We did not use any empirical data when generating these simulations. It's all from first principles in terms of representing the market as best we can, including these order types, the matching algorithms, order books, and then assuming just noise, essentially, for the actions taken here. And apparently this was enough to generate the, at least, heavy tail returns distribution, right? Something else is the linear unpredictability of return time series. Once again, shown in the literature, why this would be important is that knowledge of past events cannot help predict future movements. Big movement today doesn't necessarily imply a big one tomorrow, right? Once again, verified with empirical data, contrasted with geometric Brownian motion, and then our simulation. Something that's a little interesting here is that this test doesn't necessarily hold for extremely short lags, right? So it's a byproduct of just microstructural effects. That bid-ask bounce is gonna make it seem like there is some sort of negative correlation. A buy now, a little more likely to be a sell later, right? That's what we observe, and something that I also see in our simulation versus non-geometric Brownian motion. Nonlinear dependence is where there's significant positive autocorrelation or a persistence and volatility of returns. A big price movement today, or very volatile day is going to be followed most likely by another high volatility event, versus low volatility events are probably going to be followed by another low volatility event. Something observed in literature, verified empirically, Apple returns for various nonlinear functions, not seen in geometric Brownian motion, and observed in our case for just our baseline implementation. Last one I'm going to show, gain-loss asymmetry. This is it's an inverse statistic, essentially the distribution of first passage times. So the time it takes to hit a fixed return level. Normally we'll see more likely that, and there's an asymmetry here, so normally it's faster to lose money than it is to gain money, and something that's seen in literature, empirically, not as much, and something that we are, at least we think, able to capture. We're going to need more analysis here and then fitting a maximum likelihood fit to the actual curves to get a better idea of, are we getting any asymmetry? But at least for now we can say, at least for capturing the properties, better than geometric Brownian motion. Things that we don't get are things like stylized facts that are related to volume. None of our agent behaviors are even conditioned on volume, so we're not too surprised there. There's also effects that we see that are related maybe to historical price trends. Once again, our agents are not conditioned on any sort of price history. I'm not surprised we don't get those either. But if anything, we're able to sort of use this information to say, okay, maybe now we can think of things that we know we need to add in order to eventually hope to get the full spectrum of these stylized facts, of which there are many, in which we are still in development of the test cases and the like. To summarize, the detailed elements of the market structure, things like the order books, decisions being made in parallel, are important to modeling these financial time series, right? So accounting for these elements were needed to capture these complex behavior at the aggregate with just simple behaviors at the micro scale, right? So the simple all coming together to make this complexity emerge, right? So the intelligent agents, they did improve stability, but their inclusion did not necessarily provide any new stylized facts. This was a little interesting because the strategic behavior didn't necessarily provide any new statistical regularities, and so this made us think that, okay, maybe conditioning on the right observations, adding things to the observation space, like this information propagation, things like historical trends, these different shocks, are probably more necessary than there is in perfectly replicating human behavior, which should also be a good thing because it's probably easier to do that than would even attempt to try to model human behavior, right? So components of Brokerage.jl will need to be isolated and optimized further if we want to continue to scale this. Right now, just as a baseline implementation, all the order books are stored in one place, and they're stored in the same place as I keep the database. So big bottleneck when it comes to processing these orders, limits the amount of transactions we're able to scale to, and the like. So I guess we would like to isolate these, maybe keep if anything, this gives an opportunity to try and model, like in real life, the fragmented exchange systems. So your orders can be routed to various exchanges. There's even things about off-exchange trading. So the ability to maybe come in here and further optimize this simulation environment to include things like that, right? So lastly, the high performance and data science capabilities of Julia have already and will continue to help improve the performance of our agent-based platform. The next steps will include leveraging Julia to process these large data sets. Right now, there's another bottleneck when we scale up the number of agents, then the search for sort of agent, when they query this database, there's another bottleneck when it comes to searching this ever-growing database, and we can look into different ways to process that, maybe look at a different database architecture, or even maybe sort of make multiple brokerages, who knows. As well as wanting to generate more sophisticated agent behaviors. It's known well-known problem that the financial data is anonymized. You don't know where an order came from. And so that makes it really difficult to try and fit any sort of machine learning to learn an agent behavior. Alternatively, we could, some people have viewed maybe instead of, we just have one agent, which is just the world agent, right? And so you're interacting with this one agent, which has been trained across a whole, bunch of order book data, and then having that rely on like the whole interaction and things like that. And so we've recently been able to obtain historical data, and these are some of the things that we're looking into as some next steps. Lastly, I'd like to acknowledge my advisor, my lab mates, Polygon.io for providing the data, which a lot of this would not be possible without. And yeah, thank you all for coming and your interest. Thank you.
Do we have any questions?
Those are actually super cool. I'm a financial economist, and I do a lot of my work on market vector structure, so this is kind of fun to see. One of the things that I noticed in particular that feels very weird is like how flat the prices look.
Yeah.
Your volatility is more or less constant, which is like conditional stochasticity, meaning like volatility changes over time. These big spikes can kind of drive that. And there's a lot of interesting ways you can do that. And the fact that you have a lot of you have the ability to add heterogeneous agents basically means you can get to like ridiculously complicated. Like capture just a lot of stuff. So like one of the big ones would be like institutional trading. Like people who show up and just every once in a while they just drop these huge orders in either on like a small bit by bit basis. Like dividing up the order and just trading every 5 minutes, same quantity. That's one way you could introduce like a lot of stuff. And I missed the first part of the talk, but do you have the price sequence, like the underlying volatile value? Is that right in motion, or that's all determined by?
It's all determined by the agent. Yeah, I have seen people do that though. Goal was to, like I said, minimize the amount of stuff we add in, right? The whole idea of Occam's razor, try to be the best, and then maybe we build from there. So there is no fundamental or like underlying value. It's all, I do instantiate an initial price, but that's it.
Okay, cool.
But yeah.
I have some other comments, but
How do you handle assets leaving the market? So if the value of the asset is effectively random, what happens when it reaches a near zero value?
So the question is, how do you handle assets leaving the market, specifically when the asset is leaving the market, the value is close to zero?
Yes, that's something we've really even gotten to the point where we're thinking about that yet, right? So we haven't really seen that yet, because if anything, I guess instinctually I just set it high to minimize that wrapping, right? But no, there's a lot of things too, where like let's say something like a delisting event or bankruptcy of this company, like whatever, something that will cause it to crash dramatically. I imagine some things like that would have to, one, be added as like an external news thing that would cause it, right? And then we would have to allow for it to reach zero, right? Like right now, I might even have it as I throw an error, right? But there's a lot to think about here, right? But yeah, no, thank you.
Any other questions? All right. If none, let's thank the speaker again, and we'll set up next session.
I do think he has a good point though, which is like information flows. Like like the big takeaway from like a lot of microstructure stuff is like things that inform people about the underlying value are like critically important and like kind of one of the key drivers.
Yeah.
You kind of want some kind of like time series variation in like how people, like what people's best guess about the value is. And you get like a ton of action out of even a very simple process about just like, Poisson distributed informational events.
Yeah.
And like, that would be, I think, really easy to compute. You can just give people like a moving signal. There's like lots of ways to do that.
We've seen people do that. It's just a matter of getting to that. On the
Dude, these ABMs are very complicated. So I don't envy you. I'm Sam. Did you talk to Maureen O'Hara or not?
That's okay. There's now things that's in the article. So we've been good on board now. So this sort of first disseminating thing, right?
Yeah.
So this is for the platforms. Now going to just show up.
Yeah, Maureen's hard. You can also try Gideon Starr, who's there. I don't know if you know him. Gideon Starr. So he's in a similar field. Maureen is like super famous, and she like doesn't respond too much. Gideon is much more active. So if you want to like reach out to somebody and get some comments, he may do it, but he's kind of a theorist and he doesn't really give a shit. David. He's more of on the CS side. Maureen was kind of in charge of like a lot of the like economic part of it. But David is great. So he's a smart guy, but I've never really talked to him. He's also kind of like a theory-ish person as well. But he's great, and he's also more like CS.
Did you talk to him or something?
Yeah, I didn't talk to her.
Huh? Email?
About what? Oh, do I have? Oh, do you want my email? Yes, I can give you my email. Yeah, you've got an interesting thing here. I think there's not a lot of this in like microstructure research. Like I know of like one big paper that does kind of an Asian-based modeling thing, and they had a really simple model that ended up actually doing something similar and like representing a lot of the kind of core weird facts about microstructure. But also the order of things, like that was a big feat. They're hard to do. Yeah, they're really fucking hard. I've tried 2 or 3 and I was like, I'm tired. It's just a lot. Yeah.
Remind me, you said you're
I did my PhD in financial economics, but now I'm just doing economics.
Oh, I've seen you had a tutorial on using it for macroeconomics.
Yeah, that's me.
Yeah, I've seen it.
Okay, cool. Good. Well, good talk. Enjoyed it.
Thank you. Yep.
What are you up to now?
One more time. Oh shit.
All right, let's start with the next session. So we have Gajendra Deshpande, and he's going to be talking about fighting money laundering with Julia.
Hello everyone. Today I'll be presenting a talk on fighting money laundering with Julia. Agenda of the talk is we'll briefly see what is the forensic investigation process, then what's the double standard, and how it's related to open source, especially Julia and other languages. Then how we can perform bank account analysis or fund trail analysis, because that is the basis for our money laundering issues. Then finally, conclusion. So whenever we see any forensic investigation process, these are the steps involved: identification, collection, validation, examination, preservation, and presentation. So in the first step, the investigation officers, they are going to collect the bank statements of suspects from various banks, because the money transfers between several accounts, so they need to get the details of all these accounts. So once they do it, once they collect the statements, they need to make a copy of it. They need to convert that into unified format, because every bank has got a different statement format. They need to bring the data to unified format, and they need to save it. They need to make sure that whatever data they are bringing into unified format is not altered, is not tampered in between, because that is the important step here. The goal of forensic investigation process is to identify the evidence which can be submitted in the court of law. So if there is alteration, if there is any tampering, then court will not accept. So that's the very, very important step. So finally, it has to be submitted in the court of law. So let's see the double standard. So in United States federal law, the double standard is a rule of evidence regarding the admissibility of expert witness testimony. So there are some illustrative factors which the court has suggested. So has the technique been tested in actual field conditions, not in just the laboratory? Has the technique been subjected to the peer review and publication? What is known or potential rate of error? Do standards exist for the control of techniques operation? And has the technique been generally accepted? So in 2003, Brian Carrier published a paper. So there he examined the rules of evidence standards, including the Daubert, and concluded that the guidelines of the Daubert's tests, what we have discussed earlier, so they conform to open source tools than the closed source tools. So here, with respect to programming, we need to consider these questions. Can the program or algorithm be explained? This explanation should be explained in words, not only in code. Has enough information been provided such that thorough tests can be developed to the test of the program? Then have the error rates been calculated and validated independently? Has the program been studied and peer reviewed? And has the program been generally accepted by the community? So Julia satisfies all these conditions. So we can consider Julia as one of the languages for analysis of forensic information. So this is one of the pressing problems. So in India, in most of the recent hackathons, we are seeing this problem being given by investigative agencies. So examples of money laundering. So I'll skip this. So one of the important parameters which we need to consider is the politically exposed persons. So these are the persons who are having eminent positions in the government, maybe who are part of assembly and so on, who are ministers of the government, and their close relatives. So there is a Financial Action Task Force which has been formed in 1989 and is based in Paris, which is basically trying to address the issue of money laundering, and many countries are part of it. So this is the money laundering scenario. What happens is there are three stages basically. One is placement, layering, and integration. So in placement stage, sender splits the money into several small chunks and deposits in large amounts of bank accounts, and finally the integration happens and the money is received by the receiver. So the solution is that first get the statements from different accounts, then identify, bring it to the unified format, then you can apply Benford's law on these statements. So it gives you some idea regarding whether there is a possible fraud or no. Then generate a graph showing the different links between the accounts. Then try to predict the possible money laundering. And in all these things, you have to record each and every step. That is very, very important, because reproducibility is very, very important, because your opposition lawyer may question the things, and at that time you may have to repeat the steps and show that you are getting the results. So this is the Benford's law. So Benford's law is the first digit law, leading digit law. So there is a distribution. So the number of ones are 30%, number of twos are between 15 and 20%, and so on. So your statement should follow this. It should follow the Benford's distribution. So if it follows the Benford's distribution, then you can say that there is no possible money laundering. If it doesn't follow the Benford's distribution, then there is possible money laundering. So I have written a code here, so you can see here. Okay, yeah, see this output. So for the first case, it is not adhering to the Benford's standard. So now consider this graph. This is following the Benford's standard. So that means there is no money laundering case here. But this is how we can link. Important part, we also need logging packages. Yeah. So finally, conclusion. So fund tail analysis is very complex, and whatever I have shown, it's a very simple thing. So more advanced techniques and tools are required. Thank you.
All right. I think we've run out of some. Okay, we have one question.
Don't the money launderers also know about Benford's law?
So the question was, don't the money launderers also know about Benford's law? I think...
yeah, natural numbers follow the Benford's law. But that's the manipulation. So it can be detected. And it is just one indicative tool. So it has to be used along with advanced machine learning tools.
All right. Let's also thank the speaker once more. You're after that, right? You should do that. Thank you. Yeah, no worries. No, it's all good. It's good. Yeah. Yeah. So I'm going to be showing you timers at 4 minutes, 1 minute, and 0. At 0, we want a hard stop. Please allow me to for the live stream. Okay, that's working. You have a mic. Do you need one of those clip mics, or is that good? What's the association? Can you use the Bank of Canada? All right. So our next talk is going to be by Boyan Bejanov, and he's going to be talking about what we learned building modeling language for macroeconomics.
Thank you, everyone. So we're switching gears from finance to macroeconomics, and my name is Boyan Bejanov, and I'm presenting today on behalf of Nicolas Belsaint-Pierre and Jason Jensen. We're at the Bank of Canada, and as such, I have to make it a point that the opinions are our own and do not reflect the Governing Council of the Bank of Canada in any way. So the Bank of Canada, as you may know, is Canada's central bank, and as such, we set the interest rate as part of the monetary policy. And one of the important ingredients that goes into the interest rate decision is so-called Canadian economic projection, which is a long-term simulation of the Canadian economy running on large macroeconomic models. And the important point here is that these models are actually run by economists who are experts in their own field, which is the field of economics, but they're not necessarily experts in software development. So this is an important consideration, which we took into account when we updated our software platform for running these projections. And we publish these 3 packages which support that platform internally. So yes, numerical methods are important. We need all the numerical methods to run the simulations and all the related analysis. But equally important for us is to have this intuitive and easy-to-use interface so that the economists can wield the power of these algorithms to do their work while thinking about economics and not thinking about programming and the computers. So the rest of the talk I will, and Julia is particularly good for both of these. Like, we all know how fast Julia is and appropriate for scientific computing, but also Julia has these meta-programming capabilities which allow us to hit the second point equally well. The rest of the talk I'll just show you some examples of what we've done to that effect. So when we start with the economic model, the model is empty and we just add variables. And of course, model variables are not really Julia variables. So we can use these very simple macros to just declare variables in the model. If you had to do it with the standard API, we have to know how to create these instances of model variable in different ways for different types of variables, how to properly insert them into the model. And these are all programming details that the economists don't really need to worry about. Similar thing about model parameters. And here in addition, we have these link type parameters, which allow us to define a parameter that depends on other parameters. And this becomes really handy. In this example that I'm building here is a very simple autoregressive model, although you can run like much more complex and nonlinear large models. This is like a simple example just for clarity of illustration. Even with this simple example, there are 2 parameters in the equation. Row 1 is interesting. This is an autoregressive coefficient. Row 0 is not interesting at all. The interesting one is the steady state. So we allow the economists to set the steady state in row 1 and row 0 adjusts automatically. Once again, like, you would have to know the internals of our package to do this programmatically. The equations, same deal, but more complicated. Now we have to translate this piece of economics, which is this equation, into a piece of software that the rest of the code base can work with to do what it needs to do. And all the heavy lifting is done in this @initialize macro, where we create the necessary functions and we insert the equations provided by the economists appropriately. So they don't have to worry about these programming details. We take care of that for them. Here is all the code that we built so far, and we recommend to put it in its own module for 2 reasons. Like, one, so that it holds these extra functions that @initialize create, so they don't pollute the namespace in main, but also to emphasize the separation of here is code that defines the model, and separately we have code that works with it. Here is an example of a simulation. We have 4 periods with some shocks, and then the system relaxes to its steady state, and how fast depends on row 1, and the steady state doesn't change because row 0 adjusted automatically. In addition, we have these extra macros that can be used inside the equations blocks to create some as shortcuts for some of the most typical time series operations. And I have an interesting example here how we can add the Hodrick-Prescott filter to our simple model. This is a popular filter among economists. And we can literally directly implement the definition of the filter by using this moving weighted sum, like we spell out the coefficients, and the solver is going to invert this operator and apply the Prescott, the HP filter to A. Very intuitive and straightforward for the economists to implement this. And here is an example of a simulation with it. The last 2 examples are not about the models, but about working with actual time series data. And so with time series data, unlike timestamp data, we have a frequency. This means that the distance in time between observations is constant according to the frequency. And in order to iterate along the range of a time series, we have to be able to add 1 to a date repeatedly. And if you try to do this with the date from the standard library, it doesn't work because its operation doesn't make sense. That's the correct behavior. But if you have, in our package time series econ, the dates have frequency information. So if you add 1 to the day with daily frequency, we get tomorrow. But if it's a business daily frequency, then we get Monday. And if it's a weekly frequency, then we get someday next week, depending on the type of weekly frequency, which day of the week it ends. And the last example is how we can use the same macros for time series operations that we saw in the equations block, but this time outside of a model to process data. And this is a simple example with moving average. We can, of course, write a for loop that does the same thing, but the macro will not work in the for loop, and so we'll have to spell out the formula explicitly ourselves. So this is an example of what that calculation looks like. And finally, if you're like us and you're writing code that's going to be run by other people, and these other people are not software developers but are experts in some field of their own, then please make an effort to make their life easier. Julia's metaprogramming capabilities make it really easy to do this, so you really don't have an excuse not to do it. Thank you for your attention. And do we have time for questions?
Unfortunately, we've run out of time for questions. Do we have any though?
Just a quick question. So, I mean, like you're using the metaprogramming facilities to make it easier for other people to use, but then you're handling the machinery behind the scene. Now, how often do you get requests to change the machinery, and how do you handle that? I mean, or they're just happy with what you give them right now?
So the question is, how often do you have to change the underlying machinery to actually support the metaprogramming for front end that you support?
Thank you for this question. Our packages are quite stable by now. Like they've been published since 2020, if I remember correctly. So we have to make these kinds of changes not very frequently. But yes, it's not easy to do. When we have to do it, it's a bit of a struggle.
All right, let's thank the speaker once more. Our next speaker is Dean Markwick, and he's with the Bank of America. He's going to be talking about simulating RFQ trading in Julia.
Or the fun title, More Dealers, More Problems. So I'm a quant analyst at Bank of America, and I've been using Julia since 2015. It's all simulation data in this, and all the other compliance stuff as well. No Bank of America data is in this at all. So RFQ or RFS trading. RFQ trading is something that we participate in. So clients come to us at Bank of America and they ask for a trade of some size and some currency pair, and at the same time they're asking other people as well. So that person, when they're doing the trade, they're asking N liquidity providers or NLPs, and they're asking for a price and a size. They get all the quotes back from us at Bank of America and all the other banks, and then they trade on whoever gives them the best price. We've also got RFS, which is a request for a stream, where we're continuously providing prices for size over time, and then when the person wants to trade, they'll click the button and it will go automatically to the best provider. But overall, all the LPs are competing to be top of the stack and be the best price, so we can win the trade, get some revenue, and hopefully make a profit off that trade. The actual reality of this type of trading, though, is that we win the trade and it could immediately start losing money. So this is a markout plot. What's happening before the trade is the blue line. The market's not really doing anything. It's nice and flat. We get traded, and sometimes it goes in our favor, but most of the time it goes red and we're immediately losing money for some reason. The trade is happening at that dashed line. So we're either going long and the market starts falling down, or we're short and the market starts going up. And really, this is a big problem, and we need to work out why this actually happens. This is called the winner's curse, and in this simulated framework that we use Julia to simulate, the trade is won when the LP is at the top of the stack, but there's many other reasons you could win the trade, etc., etc. So why does the market actually move at the end of the day? This is a mathematical model that is written by a guy called Raoul Ullman from Deutsche Bank called Executing in an Aggregator, and this tries to explain why the market moves based on the number of people that are in competition with each other at a given time. There's a true price, P star, and no one can observe it, and each liquidity provider is trying to guess what P star is using their own price P, and then streaming out that P price plus some spread, which is the cost of trading, to all the people that want to trade. And now in Julia, this is very easy to simulate and really easy to build a quick model that comes up with these dynamics, and we'll use this as a playground to really explore the different dynamics in trading and what happens when the different liquidity providers change their behaviors and things around those different parameters. Some Julia code really to show how easy it is to write that code. Yeah, I like Julia. I think it makes a much nicer way to simulate these types of problems than, say, Python or things like that. So the key result, we find that when we're in competition with more LPs, that the trader actually gets a better price because they're asking more people and they're able to find out who's got the best price on the street at a given time. So if they ask 1, the cost of trading is 1 unit. If they ask 2, it's about 0.6, and that falls with each additional LP that they're asking. But this comes at quite a big cost. This is where that winner's curse comes in, and we start to find that the more people that are asked leads to this mark-out where the market moves away much faster and much quicker. So when someone asks just 3 people for their prices and the trade happens, the mark-out is fairly shallow. It still goes the wrong direction, but it's not too bad. When they ask 10, the orange line, it moves much more quicker and moves to a lower level. And then when they ask 25, it moves down further even more. So it looks like that even though there's no essential alpha in the trade or anything from this simulated framework, by increasing the number of LPs in competition, this is where that adverse market movement appears to come from. There'll be other factors, of course, but hopefully you can see that by reducing the number of people that you ask, you get slightly better market impacts afterwards. So this is a presentation I've been taking to clients and showing them and hopefully explaining different dynamics and what can help explain. But on our side, we can use it to help understand our pricing strategies as well. So let's say Bank of America and someone else are in competition with 2 other liquidity providers, and we know, or we're roughly guessing, that they're going to charge 1 unit per trade. What should we charge to win as much flow as possible, but at the same time maximize our revenue? So again, using the simulation framework, we can go through lots of different iterations and see what actually happens to the economics under this. So on the x-axis here is that spread that we're going to charge relative to everyone else. So if we charge 1, we're charging the same as everyone else, and everyone else wins 33% of the market share. So we're all winning 1 trade randomly over enough timescales. If we start to charge slightly less, our market share increases because we're winning more of the overall trading, but our total revenue is going down because we're not making as much on each trade because we're charging less. And then the opposite direction is true as well. As we start to increase our cost or increase the price we're charging, we win less, but we make slightly less as well because of that. So it turns out we can try and work out what the optimal value is, and we find that actually it's around 0.9 if everyone else is charging 1. Very basic model, very basic dynamics, but the Julia gives us the ability to build up these sorts of simulations across lots of different currency pairs and lots of different parameters that we might use. We can calibrate it to real data to understand the parameters better and really use it to help educate us in our different strategies. There's also the added benefit of moving to a more machine learning framework and adversarial behaviors. In this simple example, people are always charging 1 and they never change how they do. But in real life, we know that if we start winning more, they're going to start trying to win more as well, and they're going to change their behaviors. So we need to account for that some way, and we can build out really complicated adversarial dynamics and put like agent-based models on this type of behavior and see how we should react. So overall, I hope you're convinced that it's an interesting problem that we need to consider, and that how simple models can get us close to real-world dynamics, and that you can start from something very basic, very easy simulations, and it replicates what's happening in the real world quite well. And we use this really for ourselves, like I said, to explore the different dynamics, but also educate the clients on their behaviors and how that might help. And the Julia is just a great language to do this in because it's fast, lots of different other packages available, and yeah, I just like using Julia. Thank you. Any questions?
Can you elaborate a little bit on the winner's curse? Like why when you win a trade you immediately start to lose money?
So in this case, it's because you're the most wrong price, it appears. So you're getting that trade because you're the best price to that person, so you're sticking out from the pack. So that's why essentially you didn't know what everyone else knew, that wasn't a good trade to win, so you wasn't able to pull back, hence why the market moves afterwards.
You have to execute it.
Yes, exactly, yeah.
But then you might be sensitive, you might be scale sensitive. If I'm doing like, $100 million trade, versus I'm doing a $1 million trade because it's going to take you a while to to get the order queue right.
Yeah, so in practice, the market moving against us is partly our fault as well as we hedge out the risk. So on our larger trades, and we're going to the market and moving the market as we're hedging out that risk, it's the same sort of thing. But what this simulation is trying to show that the winner's curse emerges quite naturally from the different amount of people that are in competition rather than any other external factors in this case. So, yeah, in reality, the market moves away for two different reasons, our behaviour and also this winner's curse.
All right, any other questions?
Okay, thank you for your time, everyone.
Let's just thank the speaker again, please. Our next set of speakers is going to be Adan Mauri with UNLP, Damien Panijo, UNDAV, CONICET, Bitech, and Alexis Katch, UNGS and UBA. And they're going to be talking about accelerating economic research with Julia.
Thanks. Hi, everyone. I'm glad to be here to talk about one ubiquitous and very time-consuming task in applied economic research, model selection. It's well known that model selection is also used in many other scientific projects, but in economics, it's often used to choose among rival theoretical approaches, promoting opposite political advices. So it's particularly important in our discipline. Model selection often involves data processing methods, dimensionality reduction processes, and finally, some estimation, econometric or machine learning estimator, in order to obtain a good representation of the true data generating process. But thanks to Julia, a once unreachable family of these techniques is now available as a feasible option, and we build a package ecosystem upon this. In particular, as we can see in this image, we combine machine learning and econometric different algorithms in order to obtain a good balance between accuracy and consistency. We can then run billion of different alternative equations in seconds, in order to obtain black box comparable accuracy, but with a way transparent representation that also, in addition, meets with causal inference requirements. So the important and unique thing here is that we can make a dimensionality reduction algorithm combining econometric and machine learning processes to obtain accuracy and consistency at the same time. Well, but how it works? Long story short, there are a couple of packages, but long story short, this is very fast package ecosystem that works with a simple graphical user interface and provide significant scientific output, both in terms of databases and LaTeX document. And if we dive a little bit deeper into it, we can see in the first package that with model selection.jl, we can combine the data processing like outlier detection and elimination, filtering algorithm like lasso, and core feature selection procedures like all subset regression for both linear and non-linear estimators, to finally use machine learning and fine-tune algorithm in order to, to get the best and all the entire distribution of different estimation for the goal, for the equation goal. So this result, this model selection result, can after that be used in a model selection accelerator.jl package in order to obtain with additional input from the user about the description of his research topic to develop a LaTeX report where not only you will obtain model selection in deep analysis, but also an AI-assisted classification of related literature. But of course, there are a lot of new contributions that Adam can explain to us.
Well, thank you, Damian. Well, our new contributions can be grouped by 3 categories. First, performance, accuracy, and productivity. Well, in Julia, performance is always welcome. And despite that, we already have a very fast package that is 3,000 times faster than Stata, that is the standard for the econometrics, and 140 faster than R. We thought that we have a lot of room of improvement. First, we reduce our package dependencies, and that's reduce the installation, but also the compilation time by 40%. Also, we implement logic estimator that is 95% faster than Stata. And last, we implement a new OLS method based on matrix decomposition, new matrix decomposition, Cholesky and Cure, that increased the performance by 36%. At the right, we have a brief chart of the comparison between our solution and Stata. If you can see, the worst case scenario is that we are 10 times faster than Stata. But well, performance is not all, and we think that accessibility also is a must. So we create 2 different solutions for that. One is create a package in Stata that uses the same syntax and returns the same response as the econometrics are used to. But in that case, instead of running in Stata, it's called Julia. That sounds like a contra-revolutionary solution, but we think that for some econometrics people, there's a good way to go, since that they're not thinking about Julia if we're not presenting in a family way. But not to be disappointing, we have another solution that is the model selection GUI.jl package. That is a client-server web application, also it's a package, that shows all the commands of our model selection in a more familiar way. This could be installed by the user usual package way, but also we have a Dockerized method that allows to run the application without need anything more than Docker. So you have an empty machine, you install only Docker, you run the Docker by a public registry, and you get all the package and Julia prepared to run. Also, because it's a backend API, there are more people that can use this solution to create his own interface, such as like mobile apps or another interfaces. And they can use our a fully interactive API documentation based on Swagger to support that. Here we have an example of a common command on model selection, global separation command. They have a lot of variables. And in the right side, we have the comparison to our UI. I will play a little bit and explain the difference. And you can see, you choose the file, then the estimator and all dependent variables, explanatory variables, will be automatically picked by the file. So it's easy to use. And also all the options will be turning off or turning on, depends on the combination of the variables. It's so easy, instead that, like, remember all the commands that the model selection GSS has. At last, we will show a summary of the tasks that you want to perform, and then the results. The results then with all the raw data and also a summary TXT.
Thank you, Dan. So we've been working on different areas where we can speed up our models. We've been talking about accessibility, so you can have a better access and improve on your productivity with those packages. But we also thought that we could bring a productivity increased by having an automatic output, the LaTeX document Damian talked before. So just to show you what it would look like, this is the summary report. We have automatically done all the first report which is necessary to present. You have the one-liner to just generate all this. You have the cross-validation tables. You have the results of each variable and the comparisons and all the statistics needed so you can understand your models, and all brought to you automatically. And we have also improved on gathering the different abstracts for you. So with a one-liner, you just get all the documents. You have an automatic topic analysis and where your query is in those topics. You have automatically list of all the preferred documents, so the literature review you would need, and then you can have the different documents and the selected documents which are more relevant for your research. So not only have we shown you a preliminary document for you to work on, but also the literature review for you to read and improve on the productivity of your work. So in summary, we have make a one of the fastest packages to gather information from econometrics and machine learning. We have improved on performance and accessibility with model selection GUI. And we have also increased productivity by automatizing report generations and literature review. What are we working on? First, we think we have more to improve and get more community by making more estimators, by making better GUIs. We are working on that. We think that sometimes precision is not that important, so we are working in FP16 so we can have more speed improvements. And we are working hard also in the time to first answer. So we are working in precompiled custom Julia releases, so you have just fast also the first results. Last but not least, we want to thank our collaborators who couldn't be here. So thank you, Damon. Thank you all for listening.
Our next speaker is William Godoy, a senior computer scientist in the Computer Science and Mathematics Division at Oak Ridge National Laboratory. And he's going to be talking about JACC, on-node performance portable programming model in Julia.
So, hello everyone. Thanks for the introduction. My name is William Godoy. Today I'm going to talk about portable programming model in Julia. So I want to thank my colleagues Pedro and Jeff. Oh, sorry, thank you. Pedro did a lot of core work. It was a collaboration between the two. I'm part of the Computer Science and Math Division at Oak Ridge National Lab. So this is the overview of my talk, where the motivation, why we're doing what we're doing, some of the description of the package, how Julia new features are helping to work on this. I'm going to show some results on our supercomputer summit and frontier, and finally the conclusions and final thoughts, So, oh, by the way, I'm part of the Julia for HPC community, so check it out. We have above later. This is part of our presentation we had yesterday too. So the motivation is that performance portability might be a niche problem if you compare to the broader, landscape of computing. We run on x86, and if you buy GPUs, usually NVIDIA, right? But places like the Department of Energy, we diversify the investments, building machines that are heterogeneous, usually GPU accelerated to different vendors. So it's a requirement, And here I put the graph of the top 500 supercomputers to, realize that, yeah, we're niche of the niche, like heterogeneity, but it's coming, right? As we hit the, limits of Moore's law, we're going to see more heterogeneous hardware architectures, vendors, and all that. So this also came out of feedback from our first ever BOF at supercomputing, like, oh, what is a portable layer? Portable as in, can I write code and run it on different architectures? So you have, oh, and by the way, this is just self-promotion. So we're always looking for collaborations, check jobs, internships, and you are interested. So we are national labs, essentially, always looking for this type of collaboration, funded by all of you. Jack. So we try to explore, something that didn't exist in Julia, right? You have things like kernel abstractions to write your kernels for performance portability. But what about, something that looks like Cocos, functional programming? We talked to Valentin about it. It's like, oh, we're exploring this idea. Because in the DOE, you have things like Cocos that is funded in the DOE ecosystem. So we use a functional approach. We don't want to reinvent the wheel. You guys are doing a wonderful job with the backends, right? You have CUDA, AMD, GPU, JL. So one day we'll have access to Intel GPUs. We'll start trying preferences. So we reuse rather than reinvent. This is the motivation. This is for the scientist that comes and says, you tell me, Julia, it's easy. Can I just write the code and it will run everywhere? If you do it with CUDA.jl, it won't run on Frontier, for example, right? So what we're reusing is the capability of weak dependencies. For example, your backend is going to be, redirected depending on, your functionality will be redirected depending on the backend you choose. So that's the structure. We only support Julia 1.9 and onwards, right? This is very futuristic. And we include coarse and fine granularity parallelization, right? On CPU, typically scores. On the GPU accelerators, you have fine granularity in which you have to select, the tiling, the really, a small job kernel. I'm going to go through those slides, what I mean by that. So we want to put the word out there, really simple for science, right? And just like with Cocos here on the right-hand side, we're trying to be descriptive, not prescriptive. What does it mean? Like, oh, just give me your function, give me what you need, and we'll take care of the back end. So here you have an example, right? What are the main components? It's essentially the memory allocation and the ability of, just passing a parallel forward. These are very common in the HPC applications, world. So common mathematical kernel, Saxby, right? You just write that function. This is what you want. And then, you write this once. And then it should work on CUDA. It should work on AMD GPU. It should work on your CPU threads. That adds simplicity. So not only that, we take advantage of Julia, for example. We just alias, the array that cuArray give us, that ROCm array give us. And then, we can put variadic arguments, right? You can put your function is your function. You can pass, anything that you can. We have to overload this. I'm going to show that later, So your function is an argument, just like functors, nothing new. So internals, as I mentioned, uses weak dependencies. So if you look at one of your backends, it's going to look like this for threads. The same is going to look like this for CUDA, the CUDA implementation. You just overload, essentially. And, we also explode multiple dispatch because, okay, this is just for one-dimensional arrays. What about 2 or 3, depending on the science, right? What the scientists need, right? In Fortran, you have to also optimize this for the number of dimensions that your array have. So these are our results. As I mentioned, this is a very experimental. We expect a lot of feedback. This is more of part of our research agenda rather than development, right? We expect people to come out, have a taste of what Julia can do by just, okay, I want to write this kernel here, and run it on different platforms. So we have results. Here are the characteristics of Summit and Frontier. They both have GPUs. Summit is powered by NVIDIA B100s. Frontier have the latest MI250X GPUs by AMD. And here, what we're trying to look at is like, okay, this is not adding much overhead. This is a very lightweight layer on top of the wonderful backends you guys have put, right? So if you run on CPU threads, here higher is better, right? So blue is CPU threads. most of the computing power in these machines come from the GPU. You expect that acceleration, right? So this is why we're doing this. This is what the scientists will see with their kernels if they are parallelizable. So we grab typical examples, right? These are very common kernels, Saxby, conjugate gradients, lattice Boltzmanns, and we see that you can see also NUMA effects and things like that, depending on the nature of the kernel. So conclusions, final thoughts, we are presenting this performance portable, functor-based programming model. Think of Cocos. What if Cocos was written in Julia? These are not new ideas, but there's no implementation today. So the motivation, we try to keep programming in Julia as simple as possible, especially for scientists who don't have time to program, but to write papers, and overhead is minimal. And we want to expand it to relevant things and the DOE, especially the kernels we want. Feedback is welcome. Here is the repo, and I want to acknowledge, my sponsors, ECP, the facilities, of course, the projects that fund me, the package maintainers, and as I mentioned yesterday, if I'm missing someone, please let me know. I'm very grateful for all the job you put, and we're organizing a workshop at Supercomputing, so everyone's welcome to do that. Thank you very much. Right on time.
Thank you. Are there any questions?
What's the code complexity of Jack?
Thank you, Johannes, and I knew you were going to ask that. The question is, compared to Cocos, what is the code complexity compared to that? We are essentially banking on Julia, productivity. So Cocos is C++. Cocos is, you work for the C++ programming model with lambdas, templates, etc. We just bank on, you saw the two components. Array, it looks like a lot like, any of the arrays on the back end, and, parallel force. That in any ways, the better comparison will be with Fortran. It's much closer to Fortran because it's Julia. Yes, Simon. Yes. That's a great question. Thank you, Simon. The question is, how do you envision this being used or differently from kernel abstractions? Is that a fair? Yeah. No, so we talked to Valentin about this. It's essentially, we asked him like, this is yet another way of programming, right? Functional approach. Kernel abstraction is essentially following the CUDA model, right? CUDA.jl. It's like, hey, yeah, you don't have to write. It's like, what if you write things in CUDA that can work also on other GPUs? So it's specifically for GPUs. It's not really targeting CPUs. But as we show, CPUs are important in HPC still, right? So the way we want to tackle is like, look, it adds to the portfolio. It doesn't try to, if you're happy with kernel abstraction, of course, use it. It's well maintained. We're just scientists exploring this way of doing things and say, if it works for you, go ahead. You have a.
Maybe the question is more like, where do you see like a use case would be? I guess you said the GPU specific one, but if I'm a scientist, which one should I pick? Like where should I?
So the question is, as a scientist, which one should I pick? So if you're coming from Fortran, you're going to be very familiar with this parallel for. That's essentially a target audience. You're not necessarily familiar with GPU programming, but you're familiar with parallel force. Does it make sense?
I think the rest of the questions can be taken offline. Let's thank the speaker once more. Our next set of speakers are going to be Bhavan. He's the founder of Cameo Corporation, and Chalo, she's a data scientist. They are going to be talking about Fulra.jl, distributed computing with AI source code generation.
Okay, hello, Julia lovers. Welcome to exciting this Fulra.jl distribution computing with AI source code generation. And I'm Chalo, and it's my partner is Bowen. We come from Taiwan. Sorry? Okay, sorry. And it's good to be here and have the opportunity to share the idea with all of you. And we have been collaborating with the Taiwanese government on big data analysis for the environmental IoT. Through the data analysis and the visualization, we have to help government agency identify and recover $11 million from factory causing the air pollution. So in our environmental project, we encounter the challenge of producing a 6-year PM 2.5 analyzed report from 60 TB data. With a single computer, it would take 100 days. Additionally, the existing data clean source code was challenged to rewrite a distributed computing architecture. So to overcome this problem, we developed the Fora.jl, which reduced the data clean time from 100 days to just 1 day. So here we have the 3 decided principles for Fora.jl. The first one is simple. There's no need to write a special source code from distributing computing. Simply create a state-alone main.jl program is enough. And the second is auto. The source code automatically generated and deployed by AI. And the third one is free. Fora.jl is an open source. Let's use OpenAI's free trial API for source code generation. Additionally, the GitHub Actions provide everyone with a 20 free virtual machine. So here we have developed a website called Barang.ai, which running the Fora through an AI chatbot. So you can see, after Barang says, "Hello, Julia lovers, I'm Barang," we can start to chat with her. So, Barang, please download and unzip our environmental data analysis sample from Google Drive. Okay, so you can use your own sample data for me. She's using her default sample data and dynamically write a Julia program to download a zip file from the Google Drive. Then write another program to unzip it. But she's not just about generate source code. She can also run it immediately and show users the result. So let me tell the Barang, let's preview the first 5 rows to understand the data format to me. Oh, wow, it's cool. We can see the CSV file contains the columns for device ID, long, late, time, and value. So Barang, to ensure no data loss, we must write the code to count all CSV rows from our PM 2.5 sensors supply. Okay, you can see it's mistakes. So let's see, the source code generated from counting rows is missing the data frame package. So we may need to tell her, Barang debug. Okay, it's wonderful. Now it's correct. We can see the row numbers of all the CSV files. So Barang, all steps, including the file download, decompressions, and count of the CSV rows, must be in one single main.jl with a document ID argument. Okay, it appears that we need to provide a document ID as an argument for her to test. So Barang, please write a test program to test it. Okay, we can see. So please show me the result of the CSV file.
Wow, it's good. Okay, Barang, in order to distribute main.jl across 20 virtual machines using GitHub Actions, we must create a GitHub repository named test123. Great. Now Baran should create a GitHub Actions YAML script for distributed computing. This will instruct GitHub to process different zip files in parallel across 20 different virtual machines. Okay, Baran, please write a main.yaml GitHub action script for distributed computing. This script is maximum of 20 parallel virtual machines. It's processing 3 .id zip files. The script clones our counting program repository, test123. It sets up the Julia runtime environment using version 1.9 on each virtual machine. The necessary packages are then installed. After that, main.jl is executed on each virtual machine. Finally, the counting results are merged and output in an all-result.csv. Baran, please upload 2 files, main.jl and main.yaml, to the GitHub repository. Okay, we can see the file is already on the GitHub. Baran, please dispatch main.yaml to run it. We can visit GitHub website and clearly see 3 different virtual machines running in parallel. These machines handle everything from installing the operating system and the Julia runtime to running the counting program. In the end, they consolidate all results into one CSV file for us. Finally, Baran, please download artifacts of GitHub Actions. Okay, so we can see the final result consolidated into one single CSV file. This can be used to verify whether all the PM2.5 sensors have been functioning properly. Our code doesn't need a vacation, but you do. If you scan the QR code on the left side, you can access the public source code for the Fora project. And if you're interested in interacting with Baran.ai, please scan the QR code on the right and submit your email for a free trial. That's our sharing. Thank you so much.
Do we have any questions?
So at one point in time, you showed that there was like an error. Now, of course, you know, the OpenAI and ChatGPT interface, it's just open to hallucination.
Yes.
So that's one element, and you try to kind of like guide it through somehow.
Yes.
So how often would you come across this? And also, you could have a program that's synthetically correct. It's got everything, but then logically it's wrong. So how do you manage that?
Okay, thank you. Actually, we need to divide and conquer the big problems. So to prevent OpenAI tell us the wrong answer, and if we can write a very small piece of source code, like a function, then we write another function to test it by AI, it will more correct than a larger function. Yeah.
All right. The question is the GitHub action that you showed hosted by GitHub?
Yes, the GitHub Actions offers 20 free virtual machines, self-hosted, and you can also host your own GitHub Action runtime in Google Cloud Platform or other like AWS platform. Both will be okay.
I think any remainder questions we can take offline. And thank you for the wonderful talk.
Thank you.
Let's thank the speakers, please.
So
that concludes the talks for this session. Please join us outside for the remainder of JuliaCon.
1, 2, 3. Do I need to turn it off until then? Or?
No, it's up to you.
Okay.
I saw your talk in the morning session.
Yeah.
I'm very curious. I wanted to ask you a few questions.
Yeah, sure.
Because I'm working on similar using level set methods to simulate like 2D PDEs. So I'm curious if how much of your stuff you guys I know it's very set up for these more or less SIPs dynamics. I'm curious if it's extendable to other physical frameworks.
Yeah, well, I mean, as long as you can, as long as you have the exact setup of the I guess that as long as you can reform frame if you do a residual form, which is the case.
Yeah.
You can depends what you want to do, if it's just using AD or just making inversion.
Yeah, doing inversion.
I guess with jump is inversion, you can reframe the problem, get out from your problem to the jump problem. Then it's pretty. But then basically what we do is if you have your solver does a forward problem, and you can create a jump problem, then basically use now just AD to get your jump residual in a dot box kind of thing. So instead of then make it and then is our iterative scheme for the way where we use the residual to update the variables. You can use then the AD-generated joint residual to update for the joint variable in a very similar way. So I guess that would be the idea. Now, I don't know how to find the methods. Maybe that it's not directly extensible, but sure.
How do you find the performance of these methods just using Jacobi iterations to solve the nonlinear systems? Do you find them comparable? Because you can benefit from the scalability compared to say just using the differential equations.jl software.
Yeah, well, I guess there are two things. So the fact that the performance interesting thing is that not about the solver, but just using AD. The way we usually use it is that we use it in interior Morse code. So basically, the issue you have if you make a solver and pass it to AD, we basically differentiate through eventually iterative loop, etc. And that works, but it makes things the memory overhead is big and it's slow. So we were interested to find a way that we can do a thing and then we're free to move that object much more iteratively. And not just the methods, so this iterative approach you use as a solver. But if you don't use this acceleration thing, so for me, just simple, the scheme if you check the workshop material, there you see the schema, so that non-external code is really bad because it's like people are putting the charts and then they actually this tree second order index one. What happens to your back?
Well, it's Thank you. It's Cool Moral Friday. Is that true? Have you checked the microphone? Yeah, it works. Can you just say yes?
Test 1, 2, 1, 2.
I mean, it started like GPU bias. With GPU bias because the CPU may use other CPU something.
Yeah, I guess my workshop, well, I had a lot of like these PD simulations in the back of my head. Yeah, so I guess like I always wondered like where's the trade-off between doing that or just using like the differential equation of SciMLCon and sort of like how do you figure out whether it's like.
Well, I guess the effect is at the end is what they like to call this method of lines. So then it leaves the burden on you to do this spatialization, and then you just use their time interpreter.
Yeah.
And then they have like a true fancy time interpreter, etc.
Are the other presenters in the room for this session? Let's see. What are your names? Okay. Okay.
We have to control
Okay, great. So, let's switch on the next screen. So, screen, because it's hard to get some people.
It's not. I always go post. So, just FYI, I mean, I'm sure you've figured this out by now, but I'm going to be giving you cue cards. So when you have 15 minutes left, when you have 4 minutes left, 1 minute left, and then 0 minutes left.
Okay.
I will cut you off if you go too long.
Okay.
But anyway, I'm very excited.
So you will cut off at 0, 0?
I'll give you a 30. I mean, I'll figure it.
Because when you say 15 minutes left, it's 15 minutes for the half hour or for the 25 minutes?
Before the 25 minutes. I want to make sure that.
So after 10 minutes, basically, you show you.
Yes.
Okay.
So
there will be 5 minutes for questions, right?
Yeah. And I'll make sure to repeat the questions into the microphone before you answer, so that everyone on the stream can hear you and hear the person answer.
So you will repeat them?
Yeah, I'll repeat them. So you just have to worry about answering after I finish them. Do you have any questions?
How do you do this?
Yeah. So you're going to have 25 minutes to talk, give or take. And so I'm going to tell you when you have 15 minutes left, when you have 4 minutes left, 1 minute, and 0 minutes. And at 0 minutes, I'll probably just let you finish your sentence or whatever you're talking about, and I'll make sure to give up the floor for questions.
Okay.
When people ask questions, I'll just repeat the question for the stream and for posterity on YouTube and stuff like that, so everyone knows what your question is. And then you can answer the question into the microphone. Is there? Yeah. Hello.
What's your name?
Oh, Daniel. Nice to meet you.
It's just your tag is not two-sided.
Sorry. I'm so sorry. Hello, everyone. Please start getting seated. We're about to start our next session, the 2 p.m. session. Very happy to chair the session, and I'm happy to see this presentation on scalable 3D PE solvers by Samuel. So whenever you want to start.
All right, thanks. Yeah, so welcome everyone to my talk. It's about PD solvers in 3D in particular, and also with a focus on performance. I'm Samuel Omling, computational scientist and responsible for Julia computing at Swiss National Supercomputing Center. And my co-authors are Ludovic Ress, also here, also from ETH, and Ivan Utkin, who could not make it, also from ETH. So in HPC, one talks a lot about this, right? I guess you have seen that before. Performance, portability, productivity. This is a challenge to solve since quite some time. People try to address it. And when we talk about performance, we mean also in particular scalable performance and performance portability. So I will give you a quick overview of our global solution to that, how we address this. So the first thing is to think about algorithms, right? We don't just want to get started with an old algorithm and try to parallelize it. And so we want to have scalable data local algorithms. And so for this we use the iterative accelerated pseudo-transient method. And in the workshop that we had at the beginning on Tuesday, you have seen more about this. So I'm not going to talk about that. Then the next thing is obviously programming language. And here it's very clear what we choose. So of course it is Julia. But so why is it good? You can see on the left, by the way, that performance, portability, productivity, I put them in different colors. And on the right, you see kind of what aspect each of the part of the solution responds to. And so, why Julia? Well, it's a compiled language in a static way, basically, just ahead of time. An LLVM-based compiler gives us portability, and of course, it's very good for productivity, as you all know. Then, then we get to the next thing. So, performance and scalability. How we try to address this. We want to have automatic, shared and distributed memory parallelization and optimization of architecture-agnostic code. And again, you see here the three colors, right? And so, to achieve that, we create some HPC building blocks. And mostly for us, this is parallel stencil and implicit global grid. Then the next step is performance evaluation, because we need to know where we are, or else it's kind of difficult to say what we're doing, if it's good or not. And so we do data-centric performance evaluation, and we have come up, well, since a long time with an effective memory throughput metric. I will quickly show that afterwards. Now, this is the summary, basically, of our solution, and I will enter more in detail now. So the agenda is the HPC building blocks, then automatic stencil-specific optimizations, then the effective throughput metric. Then I will briefly present some benchmarks, which afterwards we'll look at in the results, what we get with these, and conclusions of future work. All right, so the building blocks. Now, when we had to do, or let's say, we have some projects with domain scientists, right? Ludovic, for example, and so we have certain requirements. For example, here to do ice sheet modeling, we also have another group that relies on the same building blocks, which does geodynamics, and so we have a lot of requirements. So you see here a bunch of things, right? Finite differences, finite elements, automatic differentiation, level set approach, a logical array of structs, occasional explicit low-level programming for something very specific, and then compatibility with other Julia packages, because, I don't know, for example, In the workshop we saw we need to do optimization, right? We want to use things that exist. So it should be something that integrates well in the Julia world. So now the basic building blocks are, as I said, parallel stencil and implicit global grid. So parallel stencil allows to write hardware agnostic kernels in a mask-closed fashion or in an explicit fashion. And but in particular, it allows to do automatic optimization for stencil-like computations. And now parallel stencil is something that allows you to write stencil-like things basically in the widest possible sense, because you just need to do basically a relative indexing with respect to the thread idea. It's like it's anyway common in a GPU kernel programming. Then implicit global grid allows to do distributed parallelization for staggered grid with absolutely no effort. And cell arrays is something to do to enable GPU optimized logical arrays of small arrays or structs. Now everything supports now AMD GPU since more or less recently, depending on which package. Of course, in addition to CUDA and threads. And also parallel stencil enables now high-level support for automatic differentiation. Now here is a simple example of high-level programming. So we have here, for example, a 3D diffusion kernel. You see first the fluxes. On the right you see in comments you see the equations that they're referring to. And you can clearly very well recognize the equations, right? And so what's particular here is that here the fluxes Qx, Qy, Qc, and also the dt, this is not stored in global memory when you look at this kernel. You can see that in the signature, these arrays are not passed, right? So they're not being accessed or written to in global memory. So the parallel stencil will automatically do the right thing. Even though you write it as if it was all array statements, it will compute these things on the fly. So it will only access T, Ci, and T2, right? Then the next thing is architecture agnostic allocation. So we can, with these macros, automatically allocate on CPU or GPU, depending on what you want to, where you want to run. And another important feature is hiding communication, which we can do with this simple macro here. So you see in this hide communication begin end statement. You see in the end there is an update halo, and so it will automatically split the inner point computation from the boundary region computation and do the computation completely overlapping with the communication. And so all the codes that we do like that, you can then run on a single core or on thousands of GPUs. You just switch the flag in the beginning, in the initialization. And so then when you look at it in a profiler, how the kernels, etc. overlap, you see there in red how the communication overlaps the computation. Now, second simple example, generic programming. So you can see this is another macro parallel indices where we don't have this mask close notation, but the generic one. And so here we can express with this indexes ix and iy which is basically the same as we would do in a for loop, right, in CPU programming. This index that you would get, you can express whatever you want, right? And so here, for example, we have a convolution or covariance in order to do image filtering. Then a third example, here we show how we can use low-level constructs like the thread ID, block ID, the usual thing that you have also in CUDA, etc. And with the naming conventions from CUDA to make it easy for people to understand what it is. You don't have to learn something new. And so we can allocate shared memory explicitly, etc. if you want to, right? And now the last example, we can do automatic differentiation in an extremely simple way. We just use this keyword that you see in red. We say basically what we need, where we want to differentiate to, and well, we have seen that already in the workshop, so I will not go further into detail. Sorry, one more thing. And of course, you can add other keywords for the automatic differentiation. And there is also a generic way to completely use every functionality that Enzyme supports. All right. Now, automatic stencil-specific optimizations. So we got here kind of this magic flag. You just set that and it will do it. And so it will read large arrays through shared memory and steer the register usage to keep the data on the chip whenever that's possible. Then when doing that, it will also automatically determine the launch parameters. It will, for every method, it will create some metadata about the kernel, what kind of optimizations were used. So depending on what was used as optimization, it will require, for example, more or less shared memory, right? So this will be stored and then afterwards available for the call, for the parallel call. Then we can also optimize per array very much in detail what we want to do. This is not yet part of the official API, just so you know. This kind of could be exposed. Maybe we will at some point. And so right now we have some heuristics that will automatically decide how to do things best, and so we don't need to worry about that. And so as a result, it's very easy to apply to real-world applications because it will not always use the most aggressive, most resource requiring optimization, but depending on some how many arrays you have, etc., use more or less resource-hungry optimizations. And so that way, it is really something that can be applied to real-world applications. And as I already showed before, right, this kernel where it would automatically treat everything as if it was a race. Sorry, I will not go further in that because then I would better show that thing again. I need to go further because of time, yeah. All right, last thing here. It is also compatible with this height communication feature that I showed you before, even with all these optimizations. All right, so the effective throughput metric. Very briefly, So we have some assumptions here that we have an iterative stencil-like solver, but it could actually also be many other things. Then problem size is much bigger than cache sizes, and we don't do any time blocking. And so the idea is that every iteration we need to read and write the unknown here, and only read the known. And this gives us the equation that you see on the very top. And so as we define that way the effective memory access, right, the effective memory throughput is then trivial. It's just the effective memory access divided by the time per iteration. And then these values, we can afterwards compare it to the peak throughput that one can achieve with the given hardware. We call that T-peak. And that's basically all. And the T-peak, you will measure it, for example, with stream for CPUs or something analog for GPUs. Okay, and so in the case of the heat diffusion that I showed you before, you would compute it like this, yeah? Where T would be the unknown and Ci the known. And it's important that very important, crucial that we don't count the fluxes. So as I showed you before, Qx, Qy, Qz in this code, right? We don't consider them, we don't count them, well, because we don't have to actually access them, right? We can compute them on the fly in whatever fashion. Okay, so I get to the benchmarks. So I have here a couple of benchmarks. First, parallel stencil mass close, where we have, you see in red now this flag, this magic flag activated. Then we have the same, how we would do it in array broadcasting. And afterwards, a straightforward way how you would program it with kernel programming. So here first you see how you would do it with parallel stencil, so with parallel indices, right? And then below you see just the second derivative of T, of the temperature. And so now when I go further here to the next benchmark, the CUDA benchmark, you see the only thing that changes here is how we get the indexes, right? And the same thing for kernel abstractions. The only thing that changes is how we get the indexes, so that we have really something to compare against. Okay, then the next benchmark is the parallel stencil mass close that I showed in the beginning already, where you write everything as it would be arrays. And finally, the same thing with array broadcasting, where you would explicitly write each array, the fluxes, etc., right? Okay. So these are the benchmarks. Now, I get to the results. I showed you all these, right, such that you have an idea what I'm presenting here, what the results I'm presenting. And so first at the right you see the CPU performance, which we're not so much interested in, but you essentially see, well, we get a very big improvement over array broadcasting, over general GPU programming, or also CPU programming with array programming. Then on the left in green you see GPU results. So at the very left we have the GPU array broadcasting where we explicitly create arrays for QX, QY, etc. for everything, for all the fluxes. That is the worst, obviously. Then afterwards we have GPU array broadcasting where everything is in one line, so everything is in one kernel. Then we have the explicit kernel programming, so KA, kernel abstractions, explicit CUDA, and explicit PS. And you see that all the kernels with parallel stencil got a very similar performance and quite a bit higher than the explicit ones with CUDA and kernel abstractions. And this is thanks to these memory optimizations. This, like I said, this magic flag, right? All right. Some weak scaling results. We have shown that many times. It scales very, very well. Also, on the Lumi supercomputer, here is AMD GPUs. And so I get to the conclusions. Parallel stencil enables performances close to theoretical upper bound. It enables a significant improvement over straightforward CUDA.jl or kernel abstraction.jl kernels. At least, I mean, for this one that we showed, it will not always be the same, right? And it is for sure a large improvement over array programming. And also, it allows to maintain a mass-closed syntax in multi-equation stencils. So I refer to here the one where it says, the second from the right, where it says mass-closed 5 equations, right? So here we lose absolutely no performance. Having this nice mass-closed syntax, we lose no performance compared to the explicit kernel. And particularly in this way, when you want to write explicitly our equations as we want to do, right, in real-world applications, then we get a massive improvement over array programming. Yeah, and so in general, you see here again the summary of our solution to this 3P challenge, the challenge that I showed in the beginning that we want to solve. And so last thing, future work. So we want to study and tune the performance now for new hardware. We will get Grace hoppers at CSCS very soon. We have AMD GPU that we need to study and understand, and then tune all these optimizations for that. Of course, conceptually, it will not be super different, right? But the devil is always in the details. And then also, yeah, something probably to talk about in the BOF. Rather than here, we want to fix certain issues in the backend packages, but let's talk about that in the BOF. All right. Thanks a lot for listening.
Okay, we're going to take a couple of questions. Thank you for the great presentation. Does anyone have any questions? Just for reference, I'm going to repeat your question back to you so that folks on the stream can hear.
Excellent presentation. Thank you very much. So I was just wondering, you've shown working with one grid. Is it possible to work with multiple grids if your problem deserves that?
So the question for the viewers are, you've shown one grid, but is it possible to work with multiple grids if possible, or if needed?
You mean, for example, to use a multi-grid method, or?
Sure. So implicit global grid kind of assumes one grid, but does that abstraction extend beyond a single grid if that makes the math easier, if it makes more sense?
Okay. Well, so at the moment, we have not kind of implemented the things we need to set up multiple grids. But this would be pretty straightforward because we have already like an object that encapsulates a grid, right? That has all the information there. So one could easily allow to create multiple of these grids, which have their own MPI communicator, etc. I think that's what you are asking for, right? Yeah.
Great. Next question.
So I saw that you disabled some optimizations for the purpose of memory. I was asking, why did you turn off those optimizations? How did it help?
The question was, you turned off some optimizations for memory. Why was that?
I don't quite understand what you mean with that I turned off optimizations.
You were going to explain it and then you kind of skipped it. There was like a mem opt equals false that you set before your kernels. I was wondering why that was necessary.
No, it was mem opt equal true.
I see.
True. Yeah, this is to activate the flag to do these optimizations. Yeah. If it was false somewhere, I'm sorry, I made a mistake. But it should always be mem opt equal true.
Okay, one or two more. Sam?
In your explicit kernel programming for KA and CUDA, did you use local memory for those? I don't remember if you did.
No, it's exactly the kernels as you see them, right? There's always the same straightforward kernel, right? Of course, if you will make a kernel that explicitly accesses shared memory, etc., then you can get better performance, right? But the idea was to compare the same kernel between the three.
The question the question for the record was this using shared memory in the CUDA.jl version? Sorry.
Because also if you start using explicitly shared memory and so on, you deviate a lot from the equations. It's hard to see them afterwards anymore. Yeah. So we wanted to compare things where you still can see more or less the equations.
Okay. One more. Last.
When it comes to the number of threads and grid size and blocks and all that, how do you guys, I'm assuming you're presenting the best, right, combination for that. How do you guys come up with that?
So the question is, how do you come up with the number of blocks, threads, and all these things for the GPU and other abstractions?
These are all heuristics until now, basically experience on what works best. Of course, also based on certain knowledge what should work best. And in terms of problem size, in general, we use always big problem size, right? But again, all the benchmarks use the same problem size, right? So it's not that one had a bigger than the other, right? So we use big problems because with GPUs you will not get good performance for super small problems. Yeah? So it's not always that the largest possible problem size will give the best performance, but it has to be big.
Okay, great. I know there are a couple of more hands up, but we have to move on to our next speaker. So catch him after the talks if you want to ask him more, I suppose. Thank you.
Okay. Can you press F1, F11?
See.
It has the touch bar.
Oh.
Okay.
Yeah.
I think should find. I'm not sure where it's.
Yeah, I think it'll. I mean, can you go through to the next slide and everything?
She could go to the 3 dots. It's called the dots.
Right. It's trying to find the 3 dots or something.
Yeah. There you are.
In some area.
Yep. There. Full screen.
Or if you guys okay, maybe I can.
This is
just
fine.
use it.
This is
Yeah.
fine. Okay. We'd like to thank our next speaker for presenting Young Sung Kim on accelerating migration of Fortran and C simulations to Julia. Whenever you're ready.
All right, thank you for the introduction and thank you for joining. This talk is about how to migrate the large scale and also already existing simulation application to Julia. And also I will introduce a new Julia package called excelinterface.jl to support that kind of migration. This is a collaboration work between myself and my colleagues at Oak Ridge National Lab at Dr. Hyun Kang and Dr. Sarath Sripathi. All right. Okay, so at the heart of the high-performance computing, we believe that there's a large-scale simulation. Lots of scientific researches these days rely heavily on those large-scale simulations. Traditionally, we have used the Fortran or C or C++ to write those applications, and still, those 3 languages are widely being used in practical usage. And if you see the left plot, I got this data from one of the NERSC slide that it shows around 50% of users are using those traditional, we call compiler-based languages. And if you see right pie chart, it shows what are the languages that are used as a principal code languages in ECP applications. If you're not familiar with the ECP, it's an exascale computing project by the US government to prepare the exascale computing hardware and software. And they want to make sure that the application is ready for the next generation supercomputer, which has mostly the GPU. So they try to transform the traditional CPU targeted application to the GPU targeting applications. These days, computational scientists are facing, I think, we believe, the 2 challenges. On one side, they need to rewrite their code to run their application on GPU. Most of top-tier supercomputers around the world get their computing power from GPU now. And they have to use the GPUs at the new machine if they want to compute their application or their model to others. So that's something eventually they have to do. On the other side, they also need to think over how to integrate their Fortran or C code seamlessly toward the AI and machine learning. Of course, AI and machine learning is a huge trend these days, and even in trend in the academia or the research area, as though if they want to secure their funding, somehow they need to find out some way to tap into the AI and machine learning. So these are the 2 trends they have to think about. These are challenges to the computational scientists and traditional kind of computing area. But again, in reverse, it could be a very good, precious opportunity to others like a Julia community. Why? Let me explain that a little bit more. So you have Julia, and I think Julia has very unique and strong opportunity and position as a primary HPC language. Is first very fast. Sometimes, I apologize. It's a fast, even sometimes it's faster than Fortran. We already have seen some, the cases in this conference. And also it has quite good lineup of the AI machine learning packages and support and community. And also it's Julia community diligently add support for new GPU hardware. So it has all of those. So it's a very good opportunity, and it has a very good position to be a new next generation HPC primary language, I think at least, and we think. The line plot that I created is the comparison of the performance between Fortran implementation and Julia implementation, one with a bound check, another one without bound check. And we port mini weather, which is the kind of simulates flow, weather-like flow, and it's very widely used as a comparison of the benchmarking. It did show that the solid blue line is a performance result from Fortran version, and the other two lines are Julia version. As you can see, the lower is faster, and you can see there's a green dashed line that is faster than Fortran version with all cores in one node. So I personally also experienced that too. Okay, so yeah, we ran that on our newest machine on Oak Ridge, which is a Frontier machine, latest AMD CPUs. So how Julia can become a primary HPC language? I think there are two paths. One path is to completely rewrite. Create the new simulation entirely from scratch in Julia. So we have seen Climber, and yesterday I learned that there's a Trixie. It shows really a fantastic performance and also scalability using entirely within the Julia. So it's very impressive. But there's another way that we may want to rewrite the existing Fortran C or C+ code that is widely already using in the supercomputing center. We don't need to choose either one of those. We can, of course, try both of ways. But my argument here is that if we just want to focus on the left path, which means that to just create everything in the Julia, it may take a little long or takes a lot of time to become a primary language because it takes a lot of time to convince scientists to move towards the Julia. So my argument here is that without Julia community focusing on the right path, it might not be very difficult to take time or may not be even possible because the conventional Fortran C++ developer also working on how to bring the GPU programming or AI things in their language itself. And who knows, new language comes out, say, Alice, and they can handle those things. So I think we need to kind of at least put our attention on that path too. But actually, it's very difficult to rewrite the already existing code to Julia, or in general, any language from one language to the other language. Let me explain that by taking the example of E3SM, which I'm most familiar with because I'm part of that project. E3M is a high-resolution Earth system model. It's to study a variety of climate-related problems. There are a lot of different components, which is essentially quite different component in one under the hood. And it's open source, so everybody can download. At the same time, everybody can contribute to. Mostly written Fortran. Some code is just some decades old. Some is very new. Some new code is for the rewriting for the GPU. And it's 1.8 million lines of code without any comment or any blank lines. If we include the direct GitHub server modules. The lines goes high up to the 3.5 million lines. If you look at GitHub statistics, about on average 15 commits to the master branch every day. And there are about 400 participant members, and there are 88 accompanying GitHub repositories. Of course, not all repositories are active, but still there are many active repositories there. So considering all of this is really difficult to rewrite. First, it's very complex and complicated. There are many domain-specific algorithms, which is really hard to understand what's going on in the code if you are not the expert in that area. And there are many initial configurations which make the program itself is really behave differently. And also, nobody knows everything. One component developer doesn't really know how they make the other component. And there are a lot of different language skills required, a lot of work because there are a lot of lines of code, and also management could be messy because there are different projects ongoing at the same time. They have to manage if they want to rewrite. And also, it's a moving target. They keep adding. Scientists doesn't await, a software engineer to rewrite our code. And also, there's a lot of human factors that there's simple fear of migration failure. Some statistics say that there are about 70% of migration fails. Of course, it's not scientific field, the other field, but there's, some people say that. And also, there's a diverse interest. So all in all, it seems really, really difficult and looks impossible. But I think there could be one possible viable way is just reusing existing code base. I think this is the only viable strategy we believe that is possible. So we wrapped the original code with the Julia language. So main part is driver code is the Julia language, and then the other part is just reused original code. So it's less effort, less time consuming, less disruptive, and less fearful. At the same time, because we can put the data in the Julia array, we can get benefit of the Julia ecosystem, immediately. Right, so technically, very simple idea is just to wrap the original code in the shared library and make a call from Julia main to the function in the shared library using Julia C code. And we, of course, need to use the external compiler to generate the shared library. So it seems quite a simple idea, but in reality, it could be many barriers to approach this approach. First, to use the Julia C code interface, user have to literally specify all type information in the argument. I've shown just 10 of the argument here, but some climbing model that I'm looking is just has sometimes 50 argument or 100 arguments. So even though it can be 1 or 2 times, and then they just modify small thing, but still, as a user and the user point of view, is a lot of things they have to do. Second barrier is that there are still a lot of work required to extract compilable code from the original source code, like a code size matters. Custom build system, usually they have, it's not just a simple make file, they have their own custom build files, usually, if the size of the project is large. And there are a lot of different dependencies to the external libraries. Another barrier, because we are interested in GPU programming, we need to provide users how to share the data in the GPU memory with that is connected to the shared memory to the data in the Julia arrays. So these are the, I think, main barriers to this approach. So we created a new Julia package called XLinterface.jl. It first simplifies the C code interface. The previous example is shown above, and then we just created a Julia macro that simplified the interface because Julia has all the information is there. So we just generate those information on the fly and then create the SQL interface under the hood. Of course, there's some overhead, but because usually there's a loop and the code does not change any type information in the middle, we can just reuse the cache. So there's no real penalty if you reuse multiple times. Secondly, the package we call J generate the shared library automatically. So if you look at left side in the blue box, there's a Fortran code. We just copy that dashed box part into another text file. Or you can put that in the string. And then we created the JKernel macro that read those text file, all the body part of the Fortran function, and then add additional part of the code to make sure that it's compilable, and then generate the shared library, and then compile and then load and make a call on those process on the hood automatically. So it's just simplified how to generate shared library, how to use the shared library, those things. And also, it simplified the GPU data exchange. If you look at the green box, there's another J macros that seems similar to OpenMP or OpenACC-like. We intentionally create the interface, user interface, similar to the OpenMP and OpenACC-like, because that's what they usually the scientists, computational scientists, familiar with. With that, J automatically translate those information to the programming framework on the hood, which of the selected in that part in that situation. If that's the CUDA, then generate CUDA code. If it's the OpenMP target, it generates the OpenMP target. So that data exchange part is handled also. All right, to demonstrate the capability of J, we ported Miniweather Fortran version to many different versions of the J, like a J Fortran or J OpenACC or JHIP, and compared the performance. Miniweather is, as I explained, that is developed by one of the colleagues in the Oak Ridge National Lab, Dr. Matthew. It's really nice app that you can easily transform from the other language and compare the performance of all of those things. So the data code structure of the Miniweather is like this. There's an initial part, initialization part, and go into the main loop. And in the main loop, there's a compute the flux, compute tendency, and update the fluid state, and the write output, and then return back to the loop. So we ported that to Julia and also J. Initialization part, it creates the array, and then it's populate the array with the initial condition. And then in the main part, the main algorithm, like a compute flux and compute tendency, all those things, is we just copy and paste, basically, as I shown previously. So you put in the different text file, and then it can be read by the J. So it was very quick. You just copy and paste. Literally, we haven't changed it. So first case I want to demonstrate is the migration from Fortran to J Fortran. As I said, that we just copy and paste. So we was able to create all those nine kernels almost immediately, and the performance like is shown like here. The blue solid line is the Fortran version, and dotted line is a J Fortran version. As you can see, the performance is getting closer as the size of the workload is larger. Okay, the next key I want to show is we don't want to satisfy with the Fortran version. Of course, we want to run that on the GPU. So we want to transform to the HIP version, but it was it is usually very hard to port to heap all other GPU language, everything at once. So we want to migrate gradually, one by one. So I want to demonstrate here that it's possible that gradually migrate on one framework to another framework. So we ported 3 kernels, and the performance is a little bit slower. It's because one reason is that we used 8 CPUs instead. Fortran used the older cores of 56 cores. Not CPU, sorry, it's a cores in one node. And also there's some overhead of the data exchange between GPU and CPU. And again, we added more 2 kernels in the heap. Now the performance is getting faster with the mid-size and the larger size. And we gradually and finally migrate all kernels to heap. And now it's faster, and the fastest almost in many sides of the data regions. Okay. The third case I want to show is the migrate to the OpenACC case. First thing I want to show is how easy we can migrate to from one, add another migration in this J kernel. What we did is just only put that blue background lines, just add the OpenACC annotation, and then in the header part, we put the name of the framework, in this case, Fortran OpenACC. Then the J just picked that information and generate a source shared library from that. Another thing I want to explain here is that the way how we put every types of the kernels in one text file, which means that we can load each of those kernels at the runtime. So we generate these kernels shared library at runtime. So when you can just select any of these things at the runtime. For example, at the workload is small, Fortran is faster, then we just use Fortran kernel. But if the size of the workload is larger, then we can just turn that to the heap or other GPU-based one. Okay. So this is performance result of the OpenACC. We use the same machine on the frontier with the AMD GPU and the AMD CPU. So it's already in the general registry. So if you have interest, then you can try. There's some URL that you can try to if you want. Okay. So let me switch gear because this one is more related to what is the benefit of the migrating to Julia. So we want to convince the scientists that migrating to Julia is a good thing. So we added the machine learning part into the mini-weather Julia version. By the way, most of the work here is done by Dr. Hyung-Kang, my colleague. So I try to my best to summarize what he have done. In the mini-weather, we wanted to train machine learning some physical phenomena. So we added a very simple machine training part in the loop of the mini-weather. In this case, he added some kind of moisture simulation and some physical parameterization, we call. And then we trained that. So left is just dry, that's the original mini-weather. And he added some moisture, some simulation, and with some physics. And then he put some small perturbation in the center of the down there. And we simulated. So it gives some kind of physical phenomena is displayed. So what we did, is we put a training model in the middle of, at the end of the loop, and created very simple deep neural network using the flux. And we trained in the online while the simulation is ongoing. And then we apply the machine we trained. The left part is the result from simulation itself. Right part is from applying the machine, trained machine. But in this case, to make a little more fun, we try to apply the higher resolution, even though we trained in the lower resolution. So try to hope that it's faster because it's higher resolution. But because very simple, very small scale, it was not faster. But that was not our kind of main focus. So that was okay. Just demonstrate how easy to include those things. Who have a code in the Fortran is not easy to do that. So as a summary, I have shown that we need to focus on the migration of the existing code to be for Julia to be a primary HPC language, and J or Julia Accelerator, the Excel interface that JL is created to support that kind of migration. All right. Yeah. Thank you, and I thank the fund that has provided me to travel and work my time to here. Yes. Thank you very much.
Okay, I think we have time for maybe one or two questions. Does anyone have any questions? Yeah. And I'll repeat it after you, just so you know.
Okay. I saw that you had to copy the contents of a subroutine, like the actual loop, right?
Right.
But what do you do with the declaration of the variables? Do you also copy to someplace? So
declaration of the variables.
The question is, how do you declare the variables for the kernels that are being read?
Because if you have a subroutine, there are two parts, right? The declaration of variables and the actual loop. I saw he copying the contents of the loop. How does he copy the contents of the declaration of the variables?
Yeah.
Okay.
Yeah. You can.
Yeah, that's a good question. That we J create that part instead of user copy that, because we can that by looking at introspect the Julia variable information, type information, and then get those type information and then put that information in that part. In that way, user does not need to understand how they make a connection between the shared library to the Julia kind of the mechanism or something like that.
But imagine that the developer has to set them through the Julia code, the types of each variable, right?
No, as I showed you, user does not need to know the type.
The developer that is using J to pull the library.
You mean the developer J myself? Yeah, of course. Yeah, of course I have to know, but that's what developer does. So we are diligently making user is life easier. So user just don't need to specify that. Just put the name of the variable here. Okay.
Okay. To keep on time, we'll move on to the next presentation, but let's thank the presenter.
Okay. Thank you.
Important moment.
So our next talk today is going to be about exploring synthesis of flexible neural machines with Zygote, and our presenter is Mishka.
Hi. This works. Thanks. Thanks for organizers of JuliaCon. And so on my GitHub, there are materials related to this presentation, slides, and the open source code and protocols of experiments. And Julia is great when you need to do something non-standard. Here we are going to synthesize neural machines And what will flow through wires is vectors represented by dictionaries. So they are infinite dimensional, but very sparse vectors with finite and usually small number of non-zero elements. And this talk has two parts. At first part, I'll explain what are these machines, and in the second part, I explain what I was doing with them for zygotes. And I am really trying to find collaborators on this. So if you transition from traditional neural net to transformers, the result is much more expressive machines, and also machines which are much easier to train. And so that's how we get the modern magic. Now, if you generalize further, you can get even more expressive machines. You can have machines in which you can write general purpose continuously deformable data flow programs. And you can have machines which can easily self-modify and do all kind of magic. But they're not optimized for training. They are too flexible. They completely don't fit any modern workflows. So Zygote, however, is very flexible, and you can use it to do at least some training tasks, and hopefully we'll optimize them better in the future. So if you think about neural computations, the essence is that you interleave linear and nonlinear computations. So you just need alternating pattern like this. And so what's the natural degree of generality? It's not streams of numbers. It's any streams as long as you can combine them with coefficients. That's what one should aim for. And so you get this very natural class of neural machines which use single neurons transform arbitrary streams. And you also, to push power further to the limit, you allow arbitrarity of activation functions. And you consider streams of tree-like objects. They are very nice to do all kinds of interesting things. And you say, okay, you have unbounded network size. So network can dynamically change. And so you have your Turing completeness because you have unbounded memory finite at any given moment. And so if you look at traditional recurrent nets, these are all numbers. And these numbers are linear combinations of this. And neurons process nonlinear these numbers inside. And we want them to become, instead of numbers, we want streams of numbers, we want this to become linear streams. And so what's interesting about linear streams, essentially, if you consider linear combination, that's essentially artificial attention. That's what attention is, linear combination of high-dimensional vector-like objects. So we are getting a situation where every input of a neuron becomes an attention device. And there are all kinds of these streams. And you can even incorporate a discrete object into them by, say, by statistical sum. And here is a typical DMM. It has multiple inputs, multiple outputs. Any input is a linear combination of output streams. And inside neurons, there can be complicated processing. And it's very powerful but cumbersome because these wires have types. This might be for one kind of linear stream, this one might be for another kind of linear stream, and you need this. And you need this type correctness condition because if they are on different types, then it doesn't make sense to connect them. We would like to have one big type which is universal and sufficiently universal. And turns out that streams of tree-like objects work well. And because they are tree-like objects, they allow us to define variadic neurons, so we want to keep track of arity either. And so we'll call them V-values for vector-like values and as a homage to S expressions. And this space, there are several ways you can look at this space. You can think about it as finite linear formal linear combinations of strings of letters. Or you can think about this as finite prefix trees with numeric leaves. Or you can think them as tensors of mixed rank. Sparse scalars plus sparse array plus sparse matrix plus sparse tensor of rank 3, for example, like here. This is an example. So these are all these different ways of looking. I am going to talk about highlighted ways. So this is scalar. This is, on this level is sparse array, one-dimensional. On this level is sparse matrix. On this level is sparse tensor of rank 3. That's how it works. And then this is your neural machine. You take all arguments of and unite them in a single tree. So now your activation function just takes a tree and produces another tree. But your linear operator works like this. It computes subtrees on this level as linear combination of subtrees on this level. And that's kind of, it takes some getting used to when you work for it. That's a bit unusual, but that's very simple, easy to implement, nothing to keep track of. And then you can program with this. There are a number of good constructions which help programming. I'll talk about some of them. And the result is that you can do things. For example, important construction is accumulator, which implements memory in a neural machine. So you take a neuron which takes some of its arguments, and you connect the output to one of this argument with weight 1. This ensures that what gets there stays there. And then you take updates on the other input. That's super important. We use it all the time, everywhere. Then, because you have more than one argument, it's easy to implement multiplicative construction. One linear combination on one argument, say, gives you a multiplier, and another one gives you what you want to multiply this multiplier by, and you get this. And you have sparse vectors of higher infinite dimension. This is example I'm going to use in the second part of the talk. Consider a neuron which accumulates a count of words in a text. So it will be a map from a token to how many times it appears. So that's a vector. And it's an infinite dimensional space because number of words is potentially infinite. But it has only finite number of non-zero elements because the text is finite. That's typical. And one can represent all kinds of data structures because you have these trees. And then these remarkable things can easily change themselves. It's a total nightmare for ordinary recurrent neural nets to change themselves because they have too few neurons compared to number of weights. But here it's very simple. You just allocate single neuron to hold the whole matrix of the whole network, and you just hold it in this neuron as an accumulator, and you take update from the other neurons, and then you can modify. Network can modify weight, can modify its own topology, can grow. And we did some very innocent things with it. We just made the network to propagate waves through its own matrix. We just run some random networks and observe interesting dynamic systems. And we just use it to do live coding. We told the network by editor, send the signal, modify itself this way, and it changes while running. But people thinking more and more that the ability of AI to change it, to creatively modify itself in this way and that way holds both big promise and huge peril. And this is the quintessential way. It's the most clear formalism to do self-modification and self-improvement. So AI safety issues are very real here, and I hope that people who will play with something like this will mind them and will keep them in mind. Because who knows what will happen? I don't. Okay, so there is this promise. This formalism has nice promise. If we expect that networks can modify themselves, they should be able to learn to modify themselves better. And then you can synthesize them. It's on one hand, you have here small, compact, nice machines. You can read them and understand them. And that's like program synthesis. But on the other hand, they are defined by matrices, by continuous models. That's a very nice combination. And we hope that it will work. But how to make this hope a reality? And second part of the talk, Julia to help with flexible things. So Zygote is the first machine learning system with enough flexibility to do that without distortions. In particular, you can take gradients with respect to trees, not with respect to variables which are in arrays but you can have variables in the leaves of trees, and you can take gradients with respect to them all. Now there is some competition. JAX can do it now, and Enzyme can now do it. But I think Zygote is still, for a number of reasons, I still prefer Zygote for this. So we'll use neural architecture search to synthesize a machine with desired properties. Consider a machine consisting of modules, which are just our DMM neurons, connected with data pipelines gated by scalars, by DMM weights. And we take a large network and start training it with specifying regularization, which will press weights many weights close to zero. And at some point, we'll start gradually pruning small weights and small connections away while continuing to train. And here, so data pipelines for our task will carry streams of dictionaries. And we are going to synthesize more or less a feed-forward DMM, but with some accumulators. So there are some local recurrence still. But basically, we start with a feed-forward network where every layer fully connected to every subsequent layer. So we skip connections. And consider handcrafted. This is a handcrafted DMM which tries to detect whether there are duplicates in a text, duplicate words, or duplicate letters in a string. So here accumulator accumulates this dictionary of mapping words to their tokens to their counts. And now you take a norm of this vector and compare it to 1. And if it's larger than 1, then you know that there are duplicates. And this difference shows you what is the degree of duplication. And here you take end of symbol and take scalar dot product with this end symbol, and that's how you know how many end of symbols you will encounter. And so this can stop whenever first non-zero arrives, or it can continue and just compute this counts on the inputs. And now we are going to try to synthesize a DMM which imitates this one. And we form the following feed-forward network. Initial layer will be this 3 neurons, final layer will be output, and intermediate layers will have 2 neurons of each type, so 8 neurons. And since everything is connected to everything after it, this has about 1,500 parameters, and we are going to cut it to orders of magnitude during training. So the original network had 8 neurons in each layer, and every output of every neuron was connected to every input of every subsequent neuron. And here we only have left this because most of the things are pruned, and there is only 19 parameters here. But accumulator connections are hard-coded. We are not touching them. So that's how they compare the handcrafted. That's how they compare the handcrafted one and the synthesized one. And you can start looking at this and seeing the algorithmic interesting things the process invented and decide whether they are good or bad. It's all very readable, very analyzable, and that's how the matrix looks. This is just a v-value, this is matrix with 19 non-zero elements, weights, and that's first 5 of them. And the training was done on absolutely minimalistic data set. I took just one string, test string, with 3 dots at the end. And I was feeding one character to it every 10 time steps. So one character, then 9 empty dictionaries, then another one. Very small training sequence of 140 elements. And still it generalized greatly. It's like when you talk about short strings, it works perfectly. But within training envelope, if you start going to long strings, then you start seeing defects. But it's impressive that it works so well. I think it's a nice discovery. Okay, so that's what was done. Now I want to give a couple of slides on concluding remarks and give questions. So if you use Zygote to take this kind of gradients, don't use old style. If you use params, it won't work. Just will silently break and you won't know why. Sometimes Zygote generates code which computes gradients incorrectly. It does happen occasionally. Do include tests. Compare occasionally with numerical derivatives as a sanity check. Now, backpropagation theorem promises us that gradients are fast, no more than 4 times multiplied by number of operations which the function takes. However, this promise in practice is not always held, because very often forward code is well optimizable and overall code is not so well optimizable. So sometimes slowdown happen, and that's unfortunate, and one have to deal with it. And finally, it's great to have help from experts. It's like makes huge difference, and I'm very thankful to Mike Innes for unblocking me at one point. It's great. So this is just an exploration. It's not even a package. It's an open source prototype. And we would like to make it a technology, and I think it is. The scale of this work is such that it needs a small team. People need to think together how to do it, discuss. Like, it's not just even coding. It's people need to like get together and think what is the right approach to make. These are very tempting neural machines. It's a shame that we are not using them. It would be nice to start using them. That's why I am. And I can be contacted via GitHub by opening an issue or by email. And thank you very much for your attention. And now I'm ready for questions.
Hello. Thank you for a great presentation. We have plenty of time for questions, so if anyone wants to ask any, raise your hand. And let's see. I'll just give you the mic now.
Cool. Okay, thanks. Did you find in the structure that you ended up with at the end, are there any, is there anything redundant in there, or is it the same structure you drew out by hand?
No, it's different, and it has some quirks. For example, here we just put input in an accumulator, but here it for some reason also wants to give it ahead of time to subsequent elements. And then it really wants to propagate these things here, and we did not provide it. And instead of preserving skip connection, it abused this double ReLU compare neuron to just basically abused it as a multiplier and did it a few times. So there are strange redundancies, and the question is how to get rid of it. It's basically a starting point for exploration, not an end point. So it's not optimal.
Cool, thank you.
Did you see if this infrastructure can debug? For example, did you take one of your handcrafted models and break it and see if the infrastructure could fix it?
How do you mean again?
So take your handcrafted model, tweak something so that it's broken,
and
then use that as your initial condition. Can it fix it?
If I use it as my initial condition, then it will probably, I don't, but I would expect so, yes. I think it's easier than to train from the big one, but I didn't try now.
Let's see, you have a question?
When you say you're taking the derivative with respect to a tree, how is that different from just taking the derivative with respect to each and every single variable in the tree? And it's just, the tree is just basically a way to index each variable in the vector.
Right. But if you take derivatives separately, then it's very long, right? Because then you multiply, then you basically don't take advantage of reverse mode and you get number of your variables. So you need to take, you can probably, I thought about reshaping trees dynamically into arrays, about maintaining translation tables so that numbers are stored in flat array, and you know, I know how JAX does it. JAX as a compromise does lists of leaves which are arrays. So it depends. Yeah, I think it is possible to do all kind of optimizations here, and I don't know which one to choose. And also whatever you choose, it would be nice to have a partner or two, because it is not a trivial work.
Can you say a bit more about the sparsification? How does an edge disappear?
Oh, here is, first of all, my loss function has an L1 term. And so that's, and then if it starts getting small, it is I do control it manually. It is an attended run. It's not blind run. I do some steps. I see, do I want to cut off? So it is probably automatable. I think it is a good project to automate this attended runs. But for now, it's like sort of very babysitted run. I did not cheat. Everything is recorded, but it's not a blind thing.
Other questions? I'll ask you.
Yeah.
Oh, there's one. You. Yeah.
Yeah, thanks. So I didn't completely understand the whole mechanism, but I'm just curious in general. It seems to me like you are feeding trees to the neural network, which comes with a kind of a discrete structure. So I'm just curious about how differentiating over that even works. Like, what's the definition of federative here?
Just it's like arrays also have discrete structure. It's a grid of indexes. This is just your indexes, instead of being shaped in a rectangular regular grid, have tree shaped, and the derivative is with respect to numbers in the leaves. So it's still derivative with respect to vector, to coordinates of a vector, but the secondary structure by which we structure the coordinates is different. You can like reshape, you often in machine learning reshape between one-dimensional and two-dimensional, and here you can see the natural structure is tree-like and not regular.
Thanks.
Thank you. Let's see. Any other questions that anyone wants to ask? Let's see. Let me see how we are in time. Yeah, we have some more time. I'll ask you one last question then. I find a lot of these different AD platforms very interesting, and you kind of skim over why you use Zygote versus Enzyme or JAX, which has kind of this tree stuff going on.
Yeah,
so.
I can comment. I certainly I did JAX. JAX is what I started with because I started with Zygote and I couldn't make it differentiate trees and I couldn't get help. Then I learned to do it in JAX. But in JAX, it's really unpleasant to program. It's a nice domain-specific language. You're not programming in Python. You're programming in JAX, and yeah. But then I have this, and I found a nice issue discussing interface in Zygote, and I said, hey, I can do this in JAX. How can I do this in Zygote? And Mike Innes himself showed me how to do it. And I saw, I'm using params, and I'm stupid, and I shouldn't. And so that's how he saved me. And in Zyme, yeah, I worked with William Moses, and he held my hand. But still, my experiences in Zyme is fragile. When it falls apart, it's not like when Zygote gives you diagnostics, it gives you diagnostics. When Enzyme falls apart, your process just dies because it usually means that LLVM code is incorrect, and it's like you never know. It's I don't know if one can work really close with people like William, then enzyme probe might be great, but you need to because you then generalize, do slightly different, and something works, and now you do something else, and that now breaks. So it's enzyme is a great thing. It's a great but here you are using non-standard patterns, and they are not tested well.
Awesome, thank you. Well, if we don't have any more questions, then let's thank our presenter another time, and yeah.
Thanks.
Me? No. There is another one. Let me just double check. Yep. How do you say your first name? Shivai. What's up? Yeah. Just so you know, I'll give you a heads up with some note cards when you have 15 minutes left, and then 4 minutes, 1 minute, and 0. I'll try to, yeah. Here, I can, we still have plenty of time. We can't start before 3:30. So. What's your, yeah, so maybe I try looking up display like using silent parentheses. It should be extend. Stop here. Yeah. And now try going to that. And then try pressing the green button or the full screen button at the top left of that window. There you go. If you have F11, yeah, try F11. Or Command F11. Some control. I don't even. Oh wait, this one. Try that one.
Function?
Yeah, function F11. No.
That's right.
I think we had this issue with another person too. So. Okay, perfect. Yeah, of course. Okay, great. We have our next speaker. I think we can start. Yep. Shivai Lamba on machine learning on server side with Julia and WebAssembly, right?
All right. Thank you so much for, first of all, inviting me over and being able to present over here at JuliaCon. It's really great inspiration for me. In fact, my first time ever at MIT was 4 years ago when I took part in MIT hackathon. And at that time, I was building my first ever machine learning project. So it's good to be able to come 4 years later and talk about some of the work that I've been specifically trying to implement and bringing more support for Julia and WebAssembly. So today's talk will primarily focus on what exactly is WebAssembly for those folks who might not be aware. So just a basic primer to what WebAssembly is, what's the current ecosystem of Julia and the support for WebAssembly, and finally some of the key challenges that we face with the adoption of Julia for porting it over to WebAssembly and how the future kind of looks like, because a lot of the work that has been done has kind of been shelved, and there's some good opportunity for us to kind of crack into this enigma of being able to have better support for Julia and WebAssembly. So just a quick introduction about myself. I'm Shivai. I'm a developer relations engineer at Millisearch. It's a Rust-based search engine. And I'm also a WasmEdge ambassador. WasmEdge is a WebAssembly runtime. And you can connect with me on Twitter if you wish to learn more about Julia, about WebAssembly. So that's some of the work that I've been doing of late. So just as a basic primer to WebAssembly itself, because of course some of you folks might be knowing about it, some of you might not be. So today I'll just kind of uncover some of the misconceptions about WebAssembly and what WebAssembly is, and then we'll look at the current ecosystem of Julia and how well supported it is for WebAssembly. Now, the first question that always comes to people's mind is, especially if you're not coming in from a background of WebAssembly, is that, hey, is it just a web technology and how is it related to assembly language, right? So, is it like a new Java? Is it going to be replacing JavaScript because it's a web standard? So we'll be looking at some of the historical perspective of like how WebAssembly kind of started. Now, WebAssembly, in its simplest definition, is essentially a low-level byte code system that is acting as a compilation target for a lot of different programming languages. So whether you take functional programming languages or even object-oriented programming languages, scripting-based languages, today there's support for being able to take your language toolchain, whether it's statistically typed or even dynamic typed languages, to be able to get compiled into this binary format that is super portable and runs at near native speed because of the fact that it does not have any of the dependencies. It's just your source code that gets compiled into this binary, and it's super portable. That means it's supporting multiple system architectures. So right off the bat, like one of the biggest advantages that you can get from using something like WebAssembly is the lack of dependency of your primary binary source code that might be just working on a particular system architecture. Whereas with WebAssembly, it runs across multiple system architectures. So that's one of the biggest benefits that we get. Now, as WebAssembly started back in 2017, it started originally as a way to be able to run C++ code or let's say non-JavaScript based code on the web browser, because browsers typically only are supporting JavaScript. So if you want to run some non-native JavaScript code in the web browser, you needed a way to be able to actually do that, because only JavaScript is supported. So that's where we got rise of assembly.js, and that gave eventually rise to WebAssembly, which is then coined together as a term by folks at Mozilla and a few other companies. So if we kind of look at the success of WebAssembly in the browser, we see that when we are basically able to use more stronger or more compile-friendly languages, for example, like C or C++, which are a lot faster in comparison to JavaScript, we see a lot of great use cases. For example, you could do in-browser video editing, in-browser photo editing, and like, right now we are seeing it being used in Microsoft Flight Simulator, tools like Figma or Adobe Photoshop, which if you were trying to do these operations with JavaScript, you just would not have been able to do so efficiently. But we are able to now see that they are very efficient in the browser itself. Because of being able to use the underlying C++ code that gets compiled into the WebAssembly binary, and then you can run that inside of your browser. And if we kind of look at how this kind of looks like, so this is like a basic explanation that we take either C, C++ code, Rust code. We will you will use the appropriate tooling, for example, Mscripton, which is a tool chain that allows you to convert your C++ code into the WebAssembly binary. So by using the appropriate tool chain, you'll get your source code or whatever module that you've written in C++ to get converted into the WebAssembly binary, and then you can just run it as part of your JavaScript. So you can just import it into a JavaScript file, and you can just very easily run it as part of your web application. So this provides you the polyglot environment because you can run multiple languages. You get very small binary sizes that run very effectively in the browser. But of course, the biggest question then we saw was that there are so many different advantages that we are basically getting from being able to run all of this code in the browser. So we wanted to, of course, the basic question was that can we replicate this outside the browser as well? Because we saw the great advantages with respect to performance, with respect to the portability of WebAssembly. So we wanted to take that portability and then also serve it for non-web browser applications. So that included being able to run it on the different type of edge applications, edge architectures, being able to run it in the cloud. And that is where now we are seeing a lot of use case of WebAssembly outside the browser. In fact, today, as of like 2023, there are more applications of WebAssembly outside the browser, in the cloud native ecosystem, in the server side, for being able to run like serverless functions, which are actually faster than a lot of your traditional Lambdas or like Google Cloud functions. Just because of the fact that the size of these WebAssembly binaries is so small that it takes a lot less amount of time for the cold start, which we typically see in these functions, and also, as I've already previously highlighted, the cross-architecture compatibility that we get with these binaries. So this is kind of the evolution that if we see in general in computing, that we started off with servers, we went into virtual machines, we then, of course, moved into containers, and now we are going to be seeing a lot of WebAssembly as technology that could coexist with containers, just because of the fact that it provides so many performance benefits when we are looking at from a grand scale of how effectively we could run these applications on edge. Because one of the use cases that you might probably come across is that as we see a lot of the adoption of specific technologies like machine learning, which are generally very compute intensive, if you want to run them on, let's say, edge applications or edge devices, where one of the biggest issues that we have is the resource constraint, right? They are very resource constraint in terms of the compute power that you get on these devices. So you typically have to optimize your machine learning models a lot. And that is what we can actually get with the help of WebAssembly. If we are able to actually optimize our machine learning models to be able to run efficiently on device, on edge applications. And of course, why should we care about all of this? So if you are not aware of Docker, one of the co-founders of Docker, Solomon Hykes, mentioned that in case WebAssembly actually existed back in 2008, there would have been no need for technologies like Docker to actually exist. Now, of course, he kind of then reiterated that didn't mean that WebAssembly would actually completely replace Docker as such, but both of them can work very easily and coexist together to be able to truly make a lot of functional, highly quick functional applications, because a lot of the things that you could run on WebAssembly are short functions that generally require you to be able to run them very quickly, whereas technology like Docker could take part in managing some of the larger, longer running processes. So where WebAssembly would be very efficient is short-term processes that require you to be able to run them very quickly as well. So that is the main idea behind the WebAssembly integration, and how now we are actually seeing it being integrated with technologies like Docker. So this is like one such example, right, where you take something like a Rust code and you would use cargo build, which will then compile it into the WASM file, and then you can very easily then support it across multiple system architectures. So this is just one slide that kind of demonstrates what I had showcased about the cross-compatibility of different system architectures. So right off the bat, you get support for multiple system architectures for WASM. And now, of course, when I spoke about that, how do we bring the overall compatibility of being able to run WebAssembly outside the browsers, that's on the server side? So that's where the entire concept of WASI, or the WebAssembly system interface, basically comes up. So just think of WASI as this API that basically allows you to interact with a lot of the different operating system level features or network connections, or even your file resources, because WebAssembly itself cannot actually do anything. It's in a very highly secure sandboxed model. So if you want to do any kind of operation, you have to make external system calls that allow for your WebAssembly module to actually interact with your external environment. So WASI allows you to basically do that, be able to interact with network resources, files, and all of that. And this is like just an example of how WebAssembly and Docker kind of run. I just wanted to kind of put that together for information, but we can probably skip over that. And that kind of brings us to where we are today, right? So of course, today we are seeing a lot of use case of WebAssembly outside the browser. But of course, a lot of the things that we'll focus on, the integration of WebAssembly and Julia, have been traditionally focused on how you can actually run them on the browser. And that's where we'll kind of now look at the current ecosystem of Julia and how Julia kind of has interfaced with WebAssembly as a technology. So we have so far been able to see that, there's a lot of great use cases for WebAssembly. It's highly portable. It can run your code very efficiently. It allows you to take your non-native JavaScript code, run it in the browser, run it outside the browser. So let's see that what kind of compatibility we have today with respect to Julia. Now, before doing that, it's also important to understand that how traditionally Julia is compiled, right? So, of course, a lot of you might be aware that Julia is an interpreted language. It primarily uses just-in-time compilation, and of course, the underlying architecture is C or C++ APIs that basically are the ones that are responsible for it. So whenever you take your Julia code, it will get compiled into the LLVM, which is, of course, like a compiler, and then it will be compiled into one of the executables that will be focused on just one specific system format or system architecture. So right out of that, like, you don't get support for being able to run the same Julia code on one system architecture across multiple architectures because of this entire way of how we compile Julia. So there are primarily two different ways so far that we have kind of explored in order to be able to run Julia code inside the browser. So the first one that was kind of started off by Keno Fisher, was actually an initiative that he did around 4 to 5 years back, was trying to actually run Julia inside of the web browser. And the way kind of that he approached was that he took the interpreter, the Julia interpreter, and compiled into the WebAssembly binary, and then tried to run that inside of the browser. So this is one of the approaches. But there were a lot of different issues at that time that he kind of faced, and that led him to kind of shelving off the project for quite some time. And actually, it has not been updated for the past like 4 years since we have actually, like, since we saw this. And of course, like, this was quite nice because what you see on the screenshot is the REPL, or the Julia REPL, and being able to actually run your Julia code right in the web browser. And another implementation of this was also with Pluto. You might be aware Pluto is a very well-known interactive Julia environment that allows you to interact with Julia code. Being able to actually run or interfacing that same approach that Keno took of taking the just-in-time, of taking the Julia interpreter and compiling it into WebAssembly by using the LLVM approach and using fscripten to be able to do so. So this is another example where we see how you can actually run WebAssembly in the browser. Now, one of the other approaches that is showcased, and this is actually one of the newer ones that we have seen in the past one and a half years, is basically taking advantage of some of the popular popular packages in Julia that basically include the GPU compiler or the static compiler, which basically have a completely different approach in terms of being able to compile your Julia code into WebAssembly. So this is more of the static compilation that takes place. So in this case, what we are doing is that we are not focusing on the just-in-time compilation, but we are using ahead-of-time compilation, and in which you'll basically take your Julia source code and then using the GPU compiler.jl package, you are essentially using the ahead-of-time compilation to take your Julia source code and then get your final WASM binary. So this is like one such example of a source code where we are using the GPU compiler to declare a WASM target specifically for your Julia. So this again does use LLVM, but you have the capability of defining multiple target types. So in this case, we are using a WASM target to get our Julia code to compile into the WebAssembly binary, and then you can, of course, then run it inside of the browser with the help of your JavaScript code. Works fairly well. I would recommend everyone to kind of take a look at this simulation. It's fairly well known, and you can actually see like performing fairly well, like Julia performs fairly well. But of course, there are certain caveats with this specific approach. There is no dynamic memory allocation that can take place. There is no garbage collection taking place, because those are some of the limitations that we'll kind of explore. So there are some limitations in terms of how this particular code was actually run. There are like a lot of limitations that had to be put in order to successfully actually run this particular source code. So by running these like two different approaches, so the two approaches that we took, we kind of looked at was like the Kingfisher route was to take the just-in-time the interpreter, basically the Julia interpreter, and then compile it with the help of mscripton into the WebAssembly binary and LLVM. And the other head was the static compilation, where we used the ahead of time compilation using these specific Julia libraries. But there are some subtle differences, right? So of course, the biggest one was compiling the interpreter or the runtime in the case of Kingfisher's route, or of course using these statistical tools which allow you to do statistical compilation, right? But there are some major blockers that were encountered during these approaches that kind of led to the entire Julia community kind of just shelving off working on WebAssembly altogether. And those are primarily because of the fact that at the time when these experiments were being run, WebAssembly itself was just not that advanced. So we're talking about the timeline of 2019, 2020. At the time, there was lack of proper support for garbage collection, multi-threading, which are, of course, very important because it's not as simple as taking your Julia code, compiling it into the WebAssembly binary with the help of mscripton. Julia has a lot of other components that can be very complex. Julia has a lot of different external libraries that cannot just be directly compiled into WebAssembly, right? So it's not just simply taking your Julia code and compiling it into the WebAssembly. So there is also one of the biggest issues that we still kind of face today is that there is the WebAssembly debugging, right? So debugging WebAssembly modules is still relatively hard today as we speak. And of course, when these experiments were being run, a lot of extra code was being generated that is increasing the overall size of these WebAssembly binaries. We are looking we're easily talking about WebAssembly binaries of 50 megabyte, 150 megabytes in size. And of course, as I mentioned, thread support is not there. Then dynamic linking was limited, which of course, is very important specifically. And if we talk about the stack, how stacks basically work in Julia and in WebAssembly, those are completely fundamentally different. And those are also some of the issues which hindered the approach of being able to just take your Julia code and compile it into WebAssembly. But if we also talk about how WebAssembly could be interfaced with WASI, which of course is important to be able to run your Julia code inside of WASI. So far our focus was just running Julia on the browser, which has been the core focus of the community till now. I think barely any contributions have been made, and that's what I have been trying to, or at least our peer group has been trying to also bring support for Julia on the WASI side. And one of the use cases, in case you're wondering why to actually do that, is that with the help of WASI, you could essentially run HTTP services and also run Jupyter notebooks directly as web services. So that could mean that you could take some of your Julia code, especially let's say if you're doing a lot of scientific computing, machine learning on the server side, on edge devices. You could very easily run your such Julia code on the server side with the help of WASI, right? So those are some of the implementation issues that we found that kind of correlate for both WebAssembly and WASI. So does this fundamental question then give rise to the question that, hey, is support for WebAssembly just so bad that we should we should forget about it? There is this one video this last year that was launched around Julia language and our experience with Julia and WebAssembly. So a lot of the things that I kind of covered right now go a lot more into depth about issues with the just-in-time compilation, issues with the garbage collection, the threading, the stack-based approach, or the differences in the stack-based approach that we see in WebAssembly. So this particular video kind of covers a lot in it. So I'll recommend you to kind of watch, if you want to dive deeper into it. But so of course the fundamental question is that, hey, I mean, why am I just giving this talk altogether in if the support is so bad, right? But we have to keep in mind that a lot of these approaches that we spoke about were done during 2018, 2019, and since then the overall system for WebAssembly has grown quite tremendously. So if we talk about a lot of the different proposals for WASI, for WebAssembly, specifically with relation to garbage collection, multi-threading, or the threading in general, have improved quite considerably today. And today there are proper infrastructures in place where like a lot of these proposals are now in a state where now they are being launched for production ready, like they are getting production ready. Of course, that doesn't mean that WebAssembly is very efficient and is proficient enough to be production ready at this very moment. We still kind of lack observability tools. Debugging WebAssembly modules is still relatively hard today. So of course, like if you're doing that for your Julia code, it will still be hard. But because of the fact that today we have been able to get experimental support for just-in-time compilation of support for just-in-time compilation in WebAssembly, that also means that we could take our Julia aspect, right? So if you talk about like your entire infrastructure for Julia, so there is the two major parts. There's the just-in-time compilation and your interpreter, right? So those individually could be implemented or could be ported over in WebAssembly today. Of course, again, the experimentation around this remains very limited in nature, and I hope that with the help of this particular talk, we are able to get community effort to bring in some RFPs and revive this entire process of being able to at least try out and implement not just the standard approach that we have seen so far, whether it's with respect to being able to take the interpreter, compiling it into the WebAssembly binary with the help of Mscripton, but also now try to take the approach. And here is like one such thesis by one of the undergrads at or I think it is actually the postgrad at MIT, one of the students who kind of made this thesis, and this was published just in January of this year, in 2023, so it's extremely fresh. I'll recommend everyone to look at it because it is probably the best source for understanding the current ecosystem of Julia and WebAssembly in 2023. So I'll highly recommend everyone to take a look at this particular thesis paper that was published just this year. And this is like kind of the roadmap for what the future work kind of looks like. So if we take a look at the static compilation that I kind of described, that's complete today. Being able to create user-defined functions, that actually is complete. What we see right now is being able to build a proper WebAssembly executable of the Julia runtime. That also, of course, covers the interpreter. That is somewhere in progress. So that what we mean by in progress is that implementations do exist today, but they are not by any means production ready, right? And finally, of course, we would want to ideally build a just-in-time compiler executable for WASM. That is, of course, one of the future works. And if we are able to actually build that and have the actual Julia code run inside of your WebAssembly, right, that would, of course, interface very well and have added support for being able to run it on WASI. So the open question is that, if with the current implementation that we see for Python, so if you look at the Pyodide project and how we are able to use the CGI style compilation, because of course, in comparison to, let's say, a Rust code, which could directly just take the Rust binary and execute it in WebAssembly, Python, of course, takes a different approach. It takes the CGI approach. So similarly, if we are able to use the stdin and the std out approach, we can have support for Julia in WASI. And that in turn, what would that allow us to do is, it will allow us to actually use Julia for different different type of proposals that are running today for WASM, including WASI-NN, which is basically an approach for being able to run neural networks in WASI and take your popular TensorFlow, Onyx, PyTorch models, cross-compile them, and have them effectively train them for edge applications. So you're essentially taking your machine learning models, optimizing them for being able to run on WebAssembly, and then be able to run them on different type of system architectures. So our end goal with this particular talk is that by bringing in support for Julia and for WASI, we will be also be able to take some very popular Julia-based packages, libraries for scientific computing, for machine learning, and then compile them into the WASI and be able to run them on different type of system architectures on edge devices. That would make building machine learning models capable of Julia and WebAssembly very efficient. So with that, I'll conclude. Like this is some of the future work of WebAssembly that we'll look at. But yeah, with that, I'll conclude today's talk. If there are any questions, I'll be more than happy to take them up. But you can connect with me on Twitter. Thank you.
Thank you for the wonderful talk. We have time for maybe 1 or 2 questions. Anyone? Yeah? Okay.
Thank you very much for the overview. I have a good friend who was into Rust and was just writing me like, oh, WebAssembly, is this something also Julia can do? And it sounds still like we have to wait another 5 years or something from like what I hear between the lines until Julia can really kind of do this as well. Do you have an intuition about this? Like, is it really far in the future or is it somewhere nearer?
Yeah, so I think, I mean, probably if you would have asked me this question 2 years back, I would have said, yes, we are probably 5 or 10 years into the line of bringing mainstream support for WebAssembly. But given the fact that how quickly the Bytecode Alliance, which is basically the entire open source foundation behind WebAssembly and all the different proposals, how quickly we are coming up to speed, right? And kind of filling in those gaps where we found those initially during the time in 2019 when we first saw like implementation, right? So I think we are accelerating. It's just that we need more community-driven effort to be able to run these experiments. Right now, it's just like, a few folks who are running it on the browser. Again, not a lot of support for the just-in-time compilation. So bringing in that support, bringing in the RFPs to at least try it out. I think like, if you look at like how much time it might take, I think like probably we could have some decent amount of support in the next 2 to 3 years in terms of the timeline. Just because that now WebAssembly itself as a technology is a lot more mature in comparison to what it was in 2019.
Thank you. We'll do one more question. Yeah.
So if the Julia JIT compiler is not compiled to a WASM executable, but has anyone just taken LLVM and made it a WASM executable?
Yes. So one of these particular projects that I probably showcased, I'm not sure if it is there. Actually, I didn't cover it. But if you probably take a look at this particular thesis, it actually covers one example where someone takes the LLVM and actually compiles it into the WebAssembly binary. So the experimentation for that has been run. Let me quickly check if I'm able to probably bring that up. Do we have like time for just 1 minute? Okay. So what I recommend is take a look at this particular research paper, and there's a link for LLVM compilation to WebAssembly. So you can probably take a look at that. So that experimentation has been run. So, and it has been fairly successful. Just to answer your question.
Thank you. Thank you. Let's see, do we have our next speaker here? And how would you like me to pronounce your name?
Siddharth.
Siddharth.
You can just call me Sid.
Sid.
That's fine.
Sounds good. Just so you know, I'm going to give you a heads up when you have 15 minutes left.
Gotcha.
4 and 1 minute. Okay.
4 and 1 minute. Okay.
Yeah. Right. And then a 0. Okay. Okay, while he's setting up, I'll just introduce him. This is, the next talk is on automatic differentiation for statistical and topological losses by Sid.
Can you guys hear me? Right, excellent. Okay. Hi, I'm Siddharth. I just got my PhD at Penn State, and it's my pleasure to talk to you guys about doing optimization on statistical and topological losses, and why Julia is particularly an excellent tool for this. Okay, so I want to begin by giving you some motivation for why we started looking at this problem, and hopefully, you guys will sort of see why looking at it through the lens of topology is actually a pretty useful tool, even in an area like machine learning. Okay, so for a majority of this talk, I will sort of focus on this one use case in machine learning, although the stuff that I will be talking about is not necessarily restricted to this, right? So the problem setup is as follows. So you're given a source distribution, that's the stuff that you see in orange, and you're given a target distribution that has some interesting underlying features, geometric, topological features, right? So you can sort of think of the blue points as images of different faces or images of cats and dogs where there's some interesting underlying structure that you want to uncover. And the stuff in orange is just random noise, right? And one of the sort of hot areas in machine learning right now is trying to understand how you can transform the orange points to the blue points. So you start off with useless garbage data, and then you're ending up with something that is sort of indistinguishable from true signal, right? So these kind of models are known as generative models, and they're useful for statisticians. Have looked at this for a very long time, right? And one of the primary motivations for why statisticians have looked at this is maybe the blue points are hard to sample from and the orange points are easy to sample from, right? So you start off with something easy and then you push it forward to get something that is more interesting, right? It also sheds light on the conditional relationship that you have between these two sets of points, right? So you can sort of think of the blue points as your response variable in a regression model and the orange points as the input variables, right? So, and you want to sort of understand how is the response conditionally dependent on the inputs. And you will sort of see a problem of similar flavor if you've looked at any sort of generative models like GANs, denoising diffusions, etc. If you are familiar with style transfer, where you're sort of doing an artistic style transfer, all of these problems sort of intrinsically lie on this principle, right? So this is the problem that we'll be looking at. Okay, so what am I going to talk to you about today, right? So this package effectively has 3 different functions that are where we use Julia's excellent multiple dispatch to, expand into a collection of useful tools that you could possibly use. So the first thing on the left-hand side is an abstract discrepancy, right? So it's just an abstract structure that specifies how you're going to compare 2 different probability distributions, right? So the points that we saw are known as discrete probability distributions, and you can sort of think of this as your favorite probability metric, like the Wasserstein distance, the KL divergence, whatever, maximum mean discrepancy, etc. Okay. Then that sort of feeds into an abstract loss function, right? So this is just saying, I have something that I want to make better. So how do I measure or evaluate a loss on these points in order to get something that's better? And the last thing is an abstract backprop object, right? And this is effectively what is doing all of the optimization under the hood, okay? So the optimization is happening in the last step, but in order to make sure that everything feeds into it fine, we need to make sure that the first 2 steps are compatible with an automatic differentiation engine, right? And we'll be looking at more complex and exotic examples later on. Okay, one thing that I will mention as a remark about this is that if you want to sort of get into this process somewhere in the middle. So let's say you don't really care about a discrepancy. You don't care about metrics on the space of probability measures, etc. I just want to define a loss function on a distribution and then optimize it. So you can enter in step 2 and then proceed to step 3 if you want. You can get rid of step 3 entirely and just use your favorite, optimization toolkit in Julia, right? So it's hopefully meant to be flexible for different modeling choices that a practitioner would want to make. Okay, so this is the TLDR for what this package is. All right, so I will sort of get into a little more of the math and the actual stuff that you could possibly use this for. Okay, so I'll sort of try to focus more on examples on what's happening, and maybe I'll finish a little bit early, so if you guys have some questions, then I'd be more than happy to answer some of these questions. Can you guys see the little snippet of code that's there on the screen, or do you want me to zoom in? Okay. All right, okay. So this is a basic workflow for how you do those 3 steps, right? So over here, we're going to start off with this object that's an abstract discrepancy, and this one is known as the maximum mean discrepancy. If you're not familiar with it, it doesn't matter. Essentially, all you need to know is that it takes in 2 different parameters, right? So one is a kernel, right? So the kernel is what is used to measure the similarity between the 2 different disjoint sets of points. And then we define a function in the middle that's actually doing all of the computation for how the maximum mean discrepancy is being computed. And then finally, we have the dist function, right? So this is what I had from the last slide. So we have the dist function over here, the d function over here, which specifies that, okay, for a struct of type maximum mean discrepancy, this is how you dispatch. All right? Okay. Cool. So we have this in place now, right? So we can go to the next 2 steps. So I am going to define this object that's an MMD struct, and then I define a loss function. So the loss function is going to look at a particular target. So that's my y. That's a fixed parameter in this loss function. And then I just dispatch this backprop method on it, and then it does all of the optimization under the hood. Okay? There's nothing like super novel over here. There are tons of other packages that basically wrap around Flux that achieve similar things. Okay? All right. So if I were to do this optimization process now to go from the stuff that's just noise into the signal, you'll see that it kind of does well, but not really, right? So you see a lot of those pink points that are just stragglers just hanging around over there that aren't really able to really get to the real target in the distribution, okay? But this is a well-studied object, maximum mean discrepancy, right? So it says if I run this for an infinitely long period of time, those pink points should, in principle, go to the blue points, right? But we live in a finite time world, right? And if I were to do this on a more complex problem, it would be very, very hard for us to diagnose when it's working and when it isn't, right? So if you've ever, yeah.
What is happening here? It looks like some kind of confusion.
Yeah, so essentially the pink points are being sort of pushed towards the blue points, and it's trying to do its best to mimic those blue points, right? But not really, right? And one of the main reasons why this happens is I have chosen an ill-conditioned kernel for this problem, so it really doesn't work, right? But I know that for this problem, the kernel is bad, but if I were to do this in an actual application, I have no way of knowing that, right? And this is something that happens, I don't know, like quick show of hands, how many of you have like actually trained a GAN successfully? Yeah, okay. Well, I guess that's a testament to, how complicated these problems are. All right, okay, so this in theory works well, but in practice, not always, all right? So this is where we are interested in bringing in the paradigm of topological data analysis, all right? So I won't I mean, it's almost 4:30 in the afternoon today, so I won't really bore you with the mundane details on algebraic topology. But essentially, if there's one thing you need to know about what topological data analysis is, it's a framework for extracting shape information from data, right? So in this case, we have this infinity symbol over here, and something that's fundamental to this object is the presence of those two loops, right? So I can sort of like deform the object a little bit, but I would have to do something really, really pathological to get rid of those two loops in the shape, right? So homology is this tool that essentially captures that information, right? And this is sort of what I was talking about. All right, so if I'm given a collection of points, the points intrinsically don't have any shape associated with them, right? So in order for us to make some sense for what is the shape associated with these points, we're going to have to look at balls of radius t around these points, and that now gives me a topological space that I can sort of ascribe to having a certain topology. All right, so a fundamental object in TDA is this construction that's known as a persistence diagram. And essentially what this does is, as this sort of radius of this ball grows, it keeps track of all the different topological features that are born and when they are eventually destroyed, right? So on the left, you'll see the birth of a feature. On the y-axis, you'll see the death of a feature. So if you sort of look at what's going on over here, right, you'll sort of see that at some resolution over here, I start to get a loop, right? So I have a loop over here, and it essentially keeps track of this loop that eventually dies when we get somewhere here, and that leads to this red point over here. All right? So this is effectively what topological data analysis is doing in a nutshell, but it does this for every single topological feature. Okay, so why bother with TDA, right? So the reason why it's become so popular is that it gives you a really, really effective compression and representation for the salient features that underlie a data set, right? So for example, if I gave you this object over here, which is a persistence diagram, you'll see that there are two loops, one hole, and one connected component, right? So when I look at that, I automatically know that this is coming from something that looks like a torus, right? So these are actually the points that generated that persistence diagram. It's a two-dimensional representation, but I can do this for any arbitrary, d-dimensional point clouds, right? So it sort of encodes the shape information over here. Okay, so this is why we use persistence diagrams, but the issue with persistence diagrams is that they're not really friendly with automatic differentiation engines, right? So this is the general pipeline that we're interested in. So I'm given an input point cloud, I construct a persistence diagram, and then I compute some functional on this persistence diagram, and then I want to optimize this functional. So how do we do this, right? So there are a lot of theoretical papers that say that there exists a Clark subdifferential for a persistence diagram, et cetera, et cetera. But in order to actually get your software to do it, it's a real pain, okay? But it's not impossible, right? This is sort of effectively what this package is trying to do, right? We haven't sort of invented any of this methodology to do it. It's just that Julia is a lot better at accomplishing this, right? So this is just some boilerplate code over here that I'm going to use throughout the remainder of the talk. It's just takes in an input point cloud that's X, a loss function L, and then some optimizer, and does the usual rigmarole of optimizing it, okay? So I'm going to call this function foo, and I'm going to deploy it in different parts of the slides, okay? So the first example that I want to show you is running an optimizer on the negative entropy of a persistence diagram, right? Okay, so what is this doing? This is, if I'm minimizing the negative entropy, that means I'm trying to maximize the distribution of the points in the persistence diagram. So this means that it's going to try to like shuffle points around so that it looks as uniform as possible, right? So if I were to run this algorithm on the point cloud, this is sort of what happens, okay? All right, so let's take it a step further. And now we're going to optimize the entropy, but we're going to sort of focus on optimizing the first order topological feature, right? So the first order topological features are cycles, right? So if I were to run the same method now, but on a different loss function that tries to optimize the persistence of the loops, right? This is sort of what it looks like, right? So it tries to use the same points to create as many loops as possible. Okay, so this is telling us that, okay, we're on the right track. All right, so what I've shown you right now are ways of optimizing point clouds, okay? But this isn't the only way in which you can compute persistence diagrams for topological data analysis, right? So it's not just points that have shape, but it's also different functions. Functions also intrinsically have some shape. So the way you describe the shape of a function using a persistence diagram is through this notion of what is known as sublevel or superlevel persistence, right? So it's effectively what you do is you're given a function, and then you start to look at like sublevel or superlevel set. Those are the x's for which the corresponding f of x value is greater than some level t, right? And now I start to vary t, and I end up with these interesting topological spaces where different features are born, different features die, right? So this is sort of what goes on when I do this, right? And then I can compute a similar persistence diagram over here, right? So in practice, the way this is done is that when I start to look at these level sets, I have to discretize my underlying grid, right? So I have some function that lives on a grid. So you can sort of think of this function not being transformed to look like a histogram, right? So the histograms now have these bars, right? And every time this level t touches a bar of the histogram, that cell gets activated, okay? This is a sort of intuitive way to think about the way this is done. The way this is actually implemented for computing a persistence diagram is a little more complex, right? So I'm given a function f that I want to optimize, and then I'm given this grid of some resolution r. So the function and the grid together form this thing that's known as a cube map. The cube map computes a persistence diagram, and then we have a functional on that, and then I want to backpropagate the gradients over there, all right? So again, this isn't something new that we've come up with. There are actually analytical expressions for this, for simple functionals. But if you sort of use the right tools in Julia, you can actually do this pretty efficiently. All right, so this is an example that I want to show you where we're going to do this by looking at an image as a function, right? So I have a 128 by 128 image. I can look at that as a function. I can then start to optimize the function that lives in the image. So it's going to transform the image. But I'm going to do that in a specific way, right? So in this example, we're going to look at unsupervised image segmentation. So effectively, what we're going to do is, for that image, we're going to compute a persistence diagram. And then we're going to say, okay, I want to minimize the entropy associated with this persistence diagram, right? So that means if I have some ephemeral topological features, I want to sort of squeeze them down because that's how I reduce entropy. Small little variations get crushed down, right? And then I do this optimization. Okay, so this is what you get, right? So this is an image of a cell, and I just run this for 20 or 50 maybe, 50 iterations, and then you start to see a little more structure in this image. I'm not using any deep learning architecture over here, no UNet, none of that stuff. It's just optimization of the entropy. Okay. So this is image segmentation. Another example that I want to sort of quickly run through is high-dimensional sparse regression. So this is known as image on scalar regression. So effectively, I'm given a matrix, I'm given a collection of matrices X, and my beta, that's my sort of coefficient underlying ground truth, is also a matrix, but it has some sparse underlying signal. So in this case, it's just a circle over here. But I'm going to look at this in a really, really really low signal to noise regime. So it's a 20 by 20 matrix. I only have 400 points. So the matrix is just invertible, right? The gram matrix, sorry. And I'm adding about, noise with variance 3 over there. Okay, so this is a particularly hard problem. So the way we can sort of do this is we can run just vanilla linear regression over here to see what we end up with. More popular techniques are based on lasso or graphical lasso, fused lasso, etc. In this example, I'm just going to run just vanilla lasso. But what we're going to do now on top of that is we're going to piggyback this extra topological loss on our loss function, and we're going to do these 3 different optimizations to see what happens. Right? So you can sort of see that the regression estimator is just not able to recover that signal over there. Lasso does a pretty decent job, but penalizing it with this topological loss function sort of simplifies the amount of noise that we have and also accentuates the real information that we're looking for, right? Okay. All right, so all of the examples that I've shown you right now, like entropy, etc., these are just pure functionals on a persistence diagram. Right? I haven't told you how we can go from source to the target. Right? So in order to go from the source to the target, I need to be able to compare 2 different persistence diagrams. And for this, we need to sort of look at what is known as a partial optimal transport metric, right? So if I'm given 2 different persistence diagrams, I do an optimal transport, but it's not a vanilla optimal transport. I'm allowed to go to the diagonal and not incur any cost after that. So the diagonal has like infinite mass, right? So it's known as partial optimal transport over here. Okay, so we want to be able to do propagate gradients through this computation over here, right? And this can actually be effectively done by looking at the fixed point of the SciMLCon algorithm for this. Right? So this is the first thing that you see over there. We look at an entropy regularized version of this partial optimal transport problem. And then we also have another method that's not like theoretically well-founded, but is really, really fast. Okay, so that's the second box that you see over there. And this is just like a quick and dirty benchmark over here. You can sort of see that it's about like an order of magnitude faster to use the second one. But both of them are AD compatible. All right, okay, so the way you combine statistical and topological losses now, so this is where the backprop function comes into play, right? So I have 2 different loss functions, and I want to be able to optimize both of them simultaneously, but I can't just combine them. I can't just add them because they live on 2 different scales, right? So we need to think of like novel ways to do that optimization procedure, and the backprop function has like a bunch of different methods from literature for how you can sort of do that. So I'm just going to pick one of these methods over here. So this is known as alternating backprop. If you're familiar with like splitting techniques, this is effectively just doing a splitting technique over here. It optimizes one, then it optimizes the other, back and forth. Okay? All right, so this is the example that we looked at in the beginning of the talk. Right? And this is what happens when I just add a little bit of topological regularization over there. All right? Okay, so I am running low on time, but I'm also just almost done. And I just want to close with like a couple of really, really quick remarks over here. This is still like in like pre-alpha stages, okay? Version 0.0.0.1. All right. Lots of fun things we can do with this, right? I'm sort of particularly fond of the distances.jl package. I don't know how many of you use it regularly, but I think it's a really, really well done package. And this was sort of like was one of the primary inspiration that I had for making this, where you just have like 2 or 3 different functions, and then you use multiple dispatch to depth. Okay, but it would be nice to sort of interface this with other packages. In particular, I want to sort of shout out to Eric Hansen, who wrote this excellent package called Unbalanced Optimal Transport. Oh, is that you? Okay. Okay. Oh, I didn't recognize you with the mask. Okay, well, so over there, Unbalanced Optimal Transport, you want to sort of optimize the weights and you want to optimize the support, right? And this is a sort of similar thing that we saw, like on the cubicle grid, we're sort of optimizing the weights. On the point cloud, we're optimizing the positions of the support of these measures. So it would be nice to like bring in that abstract measure and then propagate gradients into the measure in some way. And of course, implicit differentiation.jl sounds super exciting, but has issues dealing with non-vector data types. Okay, so I want to also shout out to Matteo Chufar. I've never met him, but all of this is made possible by the excellent ripsitter.jl package that he's written. It's absolutely, I mean, it's a work of art. You should have a look at that repository just to see the amount of work that it takes. And also Yusuf, Karthi, and Kush at IBM Research, where we started working on this together last year. All right, excellent. So here are some references, and these are the QR codes. You can check out the slides and also check out the package. Pull up, file an issue if you just want to like discuss something, whatever. I'd be more than happy. All right, thank you.
Thank you. Great presentation. I think we have time for maybe one question, if anyone wants to ask. Yeah. Just ask, you can just say it. All right.
So is there like one thing where AD might be extremely useful, or is there some, so to say, killer application of AD which has not been done before in this use case, so to say, with this persistent homology?
I'm sorry. So your question was, what is one killer application of AD for just persistent homology? Yeah, I mean, like all of the stuff that I showed you was just like toy examples where you just like play around with it. But I think it would be super interesting to like actually apply it to, you know, real world data sets, right? These are very novel applications that people haven't really looked at. So, you know, feel free to check out the package. If you want to, you know, just discuss something or you have some idea, feel free to get in touch with me as well. Yeah.
No, you're fine. You still have like 1 minute. Yeah, you're kind of on time. Yeah. So, just so you know, I'll give you notifications at 15 for 1 minute. Great. And then, yeah. Let me know if you have any questions. You seem like you have to figure it out. Yeah.
Yeah, I will able to find it in public. I can't find it. You know, you will do it.
I think you can't make it public. Let me do that. That's good. I'll do that.
Okay, I'm happy to welcome our next speaker for this session, Dave Kleinschmidt, talking about ONDA batches, which is for continuous, repeatable, and distributed batching. Feel free to start whenever you're ready.
Okay, thank you for my coworkers for coming to this talk and other miscellaneous audience members. Yeah, so I'm Dave Kleinschmidt. I work at Beacon Biosignals. I'm going to tell you about some internal tooling we developed called ondabatches.jl, which, like the title says, is a tool that we use for doing continuous, repeatable, and distributed batching for our machine learning applications. Okay, right. So to start, who am I? I'm a research software engineer at Beacon Biosignals. And the team that I'm on has the mandate to build out internal tooling to support the kind of quantitative and algorithmic development work that we do. And so that's the sort of ambit under which this work is being done. So who are we at Beacon Biosignals? I just yanked this from a press release because I didn't feel like recreating our elevator pitch. But yeah, Beacon Biosignals has engineered a machine learning platform designed to interrogate large EEG data sets at unprecedented speed and scale. Yeah, great. It's good, right? Yeah. Yeah, so okay, a couple things to call out here, right? EEG data sets. I'll say a little bit more about what that looks like, how we represent EEG data, the sort of structure and nature of that data. And we have this speed and scale, right? The other things to call out there, right? So we work with kind of data that's not like, you know, large language model size, but it is like inconveniently large, right? So it's not something you could put on even one large machine, right? So we do have a real need for like a genuine distributed tooling. Okay, yeah, so why did we make this? We made it because we had a couple projects where we were basically repeatedly developing the same kind of tooling to basically build batches to train our machine learning models, right? Yeah, and so we're building batches out of like basically what is annotated time series data. And I'll say a little bit more about what that means and why it's a sort of, why there's some work that's required to actually do that, right? Okay. Yeah. So the data that we work with is sort of the input data into these models is like multi-channel, regularly sampled time series data. So something like an EEG recording that's sampled at 128 samples every second, and you have a couple electrodes on the scalp, right, that are all sampling in parallel. And the sort of machine learning tasks we're talking about here are like image segmentation style tasks where the target is basically a dense series of labels. So say every 30 seconds of the data, you need to assign a label to it, right? Next. Man, this clicker is not great. Come on, you can do it. Okay. Okay, and so the input data specifically is we have this format that we developed called ONDA. In the representation of the in-memory representation is a samples, a capital S, right? And then the labels they come in natively in the form of something we call an annotation. So an annotation literally is just a time span with some sort of associated label attached to it or whatever other metadata you want, right? And so somehow we have to massage these samples and annotation tables, they're stored in tabular form, into numerical tensors that you can chuck into your favorite machine learning model, right? Come on. I'm just gonna forget about that. Okay. Okay, so, right. A little more preparatory remarks. Who is this talk for? I think there's sort of two potentially interested audiences here, right? So one, maybe you're a machine learning engineer who, like us, is looking to model large time series data sets, and you want to actually use ONDA batches or something very similar to it to build your batches to train your models, right? Two, which I think is the more likely case for this audience, well, I would say that if the majority of the audience was not my coworkers, that maybe you're interested in developing similar tooling like this, and you're interested in how we build these kind of reusable tools in an organization like Beacon, right? It's a startup, pretty small, but we still have a need for these sort of like reusable tooling that's like well documented and tested and versioned and stuff across our organization. Okay, so yeah, why might you care? Well, first of all, we actually do use this tool at Beacon. This is not like a proof of concept or a toy. This is something that we use in production for training and evaluating our models, right? And I think in the second case, right, this is a potentially useful example or maybe a cautionary tale for how to like wrangle inconveniently large data that has this similar kind of structure, and also some of the sort of the pitfalls or the nuances of doing this in a distributed setting. So how do you take something that might work locally, synchronously on a single core, and hoist it up into the cloud to make use of this great scalability of cloud resources, right? Okay, so there's going to be sort of two parts to this talk. The first part is going to be talking about the like overall design, so the constraints we were working with, the design philosophy that guided the sort of the overall structure of this package, and the basic functionality. There's going to be a little bit of an interactive demo. And the second part is going to be how do you, like I said, hoist this sort of system into the cloud to make it work in a distributed setting, either in the cloud or like on a large machine where you want to do multi-processing. Okay, so our goals when we set down this road to make this package, right, we wanted to make a batching system that was distributed because our machine learning pipelines are distributed due to the nature and the scale of our data. We wanted to make it scalable so that we could handle data sets that are out of core, and then we can like throw more compute at any kind of like batch pre-processing or featureization that we need to do, so that like the goal is basically to like computers are cheap. We should never be wasting engineering time to like work around the fact that our pre-processing and our batch loading is a potential bottleneck for the machine learning training, right? We wanted to make it deterministic and reproducible, right? So that you always guarantee to get the same series of batches, so we can actually repeat experiments in a meaningful way, right? Which turns out to be surprisingly challenging if you're doing this in a distributed, like asynchronous setting, right? We also wanted to make it resumable for the same reason. So if you checkpoint your training at a single point, but you have some state associated with the batching process, you should be able to restart the stream of batches from that exact state. So you could restart training from a checkpoint if you wanted to. Or if you needed to debug something, you could go back to a checkpoint and restart the batcher so you can like access the batches that the model actually saw when it failed or the validation loss went crazy or something like that, right? And we wanted to make it, because this is an internal tool that's meant to be used broadly across different projects, we wanted to make it sort of flexible and extensible via normal Julia mechanisms. So that what that usually means is multiple dispatch. Right? So we wanted to build in hooks so that our engineers who are actually using this tool internally to build the machine learning algorithms can like design their own batching systems and design their own weird featureization schemes and do whatever their wild hearts can imagine. Okay, good. So the philosophy behind it was that, so this is, I think, the sort of most important point, and this has become a kind of a, thing I feel like I say all the time. So the other main Julia thing I've done in my history of Julia is build SciMLCon, which has a very similar philosophy of separating the planning and execution stage. But what we want to do is separate out the cheap parts of batch building where order matters, right? So specifying what your batch is going to contain, from the expensive parts that you can do asynchronously, so the materialization, so pulling the data down off S3, doing some kind of featureization to it with all the data in memory, right? That's the first design philosophy. The second is that we want to build on top of existing tooling at Beacon specifically, because this was originally developed for internal Beacon stuff, but all the tooling we're building on is open source and anybody can use it. So what that means is we're using this package called Legolas.jl, which is basically for designing, for making like schemas that are associated with record types that you can put into arrow tables, because we store almost all of our tabular data in arrow format, right? And then those schemas are specifically going to be built on top of like onda.jl schemas, which define this sort of format, metadata format, and coding information for our signals and the annotation schema. Okay, we want to use sort of base iterator flavored patterns to generate the sequence of batches. And the reason is that we want to sort of force our users to handle the state of the batcher. We don't ever want the batcher to be something that's just happening. We want the user to actually have to explicitly say, hey, I want to get a batch from this state, right? And we also want it to be flexible enough so that it can be readily useful across different ML efforts at Beacon and potentially beyond. Okay, last thing is we want to use this is a sort of more like at a high level like package design philosophy, but because Julia has this mechanism of multiple dispatch, we want to use function calls that we control, that are defined, that we own in the Onda batches, to provide hooks where users can then go in and provide their own types so they get called with those functions, right? And the methods for operating on them to customize things like featureization and channel selection and yada, yada, yada. Okay, so great. That's all the sort of like background and design philosophy. Let's talk about how it actually works, right? So I have a little code snippet here, which is basically just a mnemonic to remind me to go and launch a live demo. So I'm going to do that. Oh no, I made a mistake. Oh boy. Oh boy. Okay, I just got to click here. Can I do this? There we go. Okay. Here's the mic stand. This part's a little less rehearsed. I wanted to put some of this stuff in the slides, but I couldn't figure out how to do it in a way that didn't drive me crazy, so here we are. Okay, let's bring this guy over here. Okay. Okay, this is a little Julia terminal here. Okay, good. Here we go. Okay, so we're going to start by loading some signals, a signals table and a labels table. And we're going to look at those a little bit. So the signals table is just a data frame, right? You can see it has a bunch of fields. we can use describe to have a look at it, right? So it has, this is basically the schema, the Onda signal schema, right? So you see a bunch of stuff about like encoding, right? So how we were going to quantize this into integer representation that we store on disk. And yeah, that's the first bit, okay? So we can use Onda.load to load one of these. So the signal row basically refers to a like LPCM serialized or whatever serialization format you want to use. It's serialized somewhere. It could be on disk, it could be on S3, it could be wherever you want. So you load it like this, and it then materializes the samples into memory, right? So you can see that this is our multi-channel time series. So the time is on the like columns are time and rows are channels, and you can see the channel labels up here, right? Channel names. That's sort of the main thing to focus on. And then there's also a sampling rate associated with this, right? Okay. So that's that. Those are our samples. So this is what the data looks like coming in. So now let's look at the labels, right? So the labels table looks like this. So it has the things to pay attention to here is that there's a span. So this is a time span, which has like this will be 30 seconds long. I'm not going to print the whole thing for you, right? And then it has like a stage label associated with this sleep stage, right? So whether you're awake or NREM sleep or whatever, right? Okay. Okay, so the first operation we do in Onda batch is that we generate something called a labeled signals table with this label signals function. So you'll see this table looks a lot like the signals table, and that's not an accident. It basically is. It's just a signals table with some extra label information glommed onto it, right? So you see it has these extra columns now called labels and label span. And so labels, if you look carefully, is itself a samples object, right? So we've taken these annotations, which are basically just time spans, like slices of the time, and we've converted them into some regularly sampled label thing that we can then use to glom together into a tensor as a objective target for our actual machine learning optimization problem, right? And then there's a time span, which is the span of the signal that these labels are associated with, because the labels don't always start at the very beginning of the recording. They might start at some godforsaken thing. We have like some data sets where they're like some weird off by one error, and they start at like 101.995 seconds or something. So there's like a 5 millisecond offset or something. So, okay, yeah. So this is what the actual labels look like. An example of what the labels look like, right? So you see now this is also again samples. This one just has one channel, and they're sort of like indicator coded. So we've encoded our stages into like UN8s, right? So like wake is 0 or 1, and REM 1 is a 2 or something. Yeah. Okay, cool. So that's the sort of that's the first level of transformation, right? We turn the annotation time spans into this sort of like time series of labels, and we attach them to the signals table. So now everything is in a nice, neat table that we can use to build our batches. And then the package itself defines one batching scheme, what we call random batches, right? And so you can provide like weights associated with the different signals, weights associated with the different label classes, right? So if you want to over or undersample some of the things, right? You can specify the number of channels that you want to sample from each signal, right? In a batch for each batch item. So we're going to be randomly sampling two channels per batch item. And then you specify the batch size, right? So how many batch items go into an individual batch. We're just doing 3 here, a toy example. And you specify the batch duration. So what this is going to do is it's going to sample from 3 different randomly chosen signals. It's going to sample 5 minutes of a random 5 minutes out of that signal and the associated labels. And it's going to glom those together into tensors that we can put into our models. Okay, right, so the next step is to define the starting state where you're going to start sampling. So for this batch iterator, the state is just a random number generator that's going to be threaded through all of the randomization calls, right? Then we call this function iterate batch, right, which is like base iterate, but it has an underscore batch because we didn't actually want to define methods for base iterate. And that returns your one batch and the updated state. And if you look at the batch itself, the batch basically has the same, very similar schema to the labeled signals table, right? With one extra column here called batch channels, right? And so like you can see for the first item in this batch, we randomly selected the CZ and CVOR channels to include in the batch. Okay, now, so that's the batch specification thing, and that's all it is doing very cheap, quick little operations on the labeled signals table. then we can call this function materialize batch, which takes the batch, which is just a table, little table itself, and creates our x and y tensors. And so the x here is like this, right? So you see now it's a, let's see, 2 by 38,400 by 3 array. So that's like 5 minutes of data sampled at 128 hertz. And it's two channels per recording, and 3 recordings that were randomly sampled. It might sample the same recording twice, by the way. But if you don't want to do that, you can define your own iterator to do whatever kind of fricked up sampling scheme you want to use, right? Okay. And the labels, the y, are also a tensor, right? So they're a, let's see, 1 by 10 by 3. So these are 30-second labels. So in 5 minutes we get 10 of them, right? And the great benefit to our users at Beacon in this package is that there's all kinds of like fiddly crap that you have to do behind the scenes to make sure that these labels are actually aligned with these samples in the data, right? Because the sampling rates can be different, they might not align perfectly, and all that stuff, right? So like one of the big benefits of having a package that does this, even so leaving aside all the distributed stuff, is that like we now have a surface that we can test and document and maintain that like removes a lot of potential mistakes that are very easy for our users to make. Right? So like one of the reasons to build this tool in the first place is to do that. Okay. Okay. There's additional functionality for like persisting. You can persist the labels onto disk or onto S3 if you don't want to. If your label set cannot itself fit in memory in whatever machine you're using to do the training, right? But we're not gonna touch that. So just for time. Okay. Let's go back to Chrome. Oh yeah. Okay. So I think the next thing here is basically another little demo. Why does this? Okay. I think I have to do this. Okay. Yeah, so I want to talk a little bit now this like extensibility functionality here, right? So let's imagine a model that requires a specific set of channels as input every time, right? So in that batch sampling thing, we were just grabbing 2 random channels so we didn't care, right? That model, that's an appropriate scheme if your model just needs like some channels, you don't care what they are, right? But imagine a model where like you need a very specific montage, a very specific set of electrodes on the head, right? But maybe you're in a world where like your data set isn't super clean or normalized or harmonized and doesn't always have all of those channels in every recording, right? So in the bad old world, right, our algorithm developer would write their own batch loading thing. We're like, oh, give me all of these channels, and like it works fine until you hit a recording and suddenly it doesn't have the channel and your whole thing crashes and falls over and you have to restart again, right? After like spending an hour waiting for all your cluster to start up and everything to precompile and yada, 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 right? So if you wanted to, you could build in some guardrails around that. You could build a little struct we're going to call 0 missing channels, where you give it a list of channels that have to be present in the input in a particular order. And then we have this hook called get channel data that is run in the materialized batch step. Right? So this is an opportunity to, once you've loaded the samples for the time span that you're trying to access, right? You can pull them down, you have them in memory, you're materializing the batch. You can then like access the channel data from that samples object in whatever way you want, right? As long as it returns a tensor, like onto batches will be happy, right? So in this case, it basically just goes to the channels that you have to have, and for all the ones that it finds that are present in the samples, it'll stick them in the output, and otherwise it'll just fill it with zeros, right? Yeah, so let's see a quick example of this, right? So I'm just gonna define this struct here, Let's create one. So I created one here that has like a bunch of real channels and then like a thing that's not a real channel. So that's not present in any of our demo recordings here, right? So if we call get channel data on the samples we loaded earlier, right? All 4 of the samples except for the not a real channels except for the not a real channel are present, right? But then you see the bottom, the 5th one is actually filled in. Okay. And so normally the way you would use this is that like you would define your batch iterator to like plug this in the batch channels field, right? So when it's iterating batches, it would plug it into the batch channels field. But instead we're just going to manually splice it into the batch we generated earlier, and then just to show you that when you call materialize batch on this, it actually does what you want. Yeah, let's see, right? Yeah, so see in this batch, like some of the, so these, the first and the third batch item don't have all those channels present, right? In fact, they only have one of the listed ones is present. And so you see they're all zeros except for this like one row here. Yeah. So this is a way that our users can, in their own package, without modifying the on-to-batch's code, hook into the way that we're actually materializing the batch and like do whatever they kind of customization they want, right? Okay, let's go back to Chrome here. Okay. Okay, so now I'm going to switch over in the last like however many minutes I have, classic running out of time, and talk about like our distributed batch loading, right? And so I want to say a little bit about why we wanted to do it, right? Which is that like, you know, different models have different requirements of the size of the batch and the structure and how much preprocessing would have to be done. So in a package like on-to-batches, which is meant to be a reusable tool across efforts, we don't want to be super opinionated about how much resources we assume our users are going to need, right? So again, we want to provide a sort of a flexible system that's of like just flexible enough to use for users to actually do the things they need to do, but not so flexible that they can shoot themselves in the foot with it all the time, right? Yeah. Okay, I think I said more about this, right? So let's talk about like how we actually go from something where we were fundamentally just like calling local functions in a REPL, which is what I was doing here, to like executing this on like 100 Kubernetes pods, right, or 10 more realistically, but right. Okay, so the first thing is that instead of having a function that like is going to return the batches, you want to stick them into a remote channel, and a remote channel is like one of the sort of like multi-processing communication like primitives that Julia provides, right? It's basically a way that you can sort of like feed values in at one point for one process and have them like access them on another. Right? And so here, like the kernel here is very similar to what the demo I was just running before, right? So you iterate a batch from a state, we're going to materialize it, and then we're just going to like put onto the channel this the combination of the materialized batch and then the state, right? Because again, we want to make sure that like users are forced to handle the state. We really want to, like, this is like one of the opinionated things about this, like we want to make it so that like, yeah, you have to handle the state. Yeah. Okay. And we wrap this all in a function, and we can remote call that function, right? So we remote call start batching with like whatever worker process we're going to use, and then we provide the arguments like this. And this returns a future, right? So like our remote call in Julia returns a future, which is something that will have the value whenever the function returns, but who knows when that would be, right? Whenever it executes and then returns. Okay. Next, okay. Okay, so that's how you're sort of hoisting the actual batch loading process into another process, right? But we have this issue now where like we want to load probably more than one batch in at a time, right? That's the sort of one of the bottlenecks we want to remove, right? And that gets a little bit trickier because now we want to make sure we're actually maintaining a fixed, predictable batch order. That was one of our design constraints, while at the same time like parallelizing the loading of the batches, right? And the way that, so this is actually not how we do it anymore, but this is sort of the initial implementation, which we cycle through the workers that are available to us, right? And then like we're gonna remote call, we're gonna iterate the batch locally on the manager process because that's cheap and fast. It doesn't take up a lot of space. And then we're gonna remote call the materialized batch function with that batch on one of our workers. And that again, remote call generates a future, right? So now we have like a bunch of futures that we generated, right, as part of this loop, and then we just go through the futures one by one, wait on each future when it's ready, when the worker is finished materializing the batch, then we throw it on the export channel. So now we sort of like have another layer of like distributed indirection here, right? This is getting complicated fast, right? This is like kind of annoying. Okay, and then that's now our kernel that we run in this infinite loop, right? Instead of just the sort of serial batch loading. Okay, great. Easy, right? So no, it's not easy, and it's pretty subtle and pretty finicky. I'm not even going to get into like how tricky it is to like make sure that errors get surfaced properly to the user, right? So that like our users, when they're running their algorithm, they're going to make mistakes and bugs are going to happen, right? And so we want to make sure that we get an informative stack trace. We don't get like a bad state, like a deadlock or something, right? Where it just stops working and you don't know why, right? And there's also a lot of like kind of annoying bookkeeping that has to happen. So you have to keep track of the future that's returned by remote call at that like start batching level, right? Just like to see if the process has failed or not. You need to hold on to the remote channel so that you can pass it off to like the actual training loop that's like consuming the batches and running them through the GPU and doing back propagation. And you have to like hold on to the batch iterator itself, right? And not to mention the state, but the state we're forcing the user to handle again. Okay. Yeah, and so like one of the other things that this package does is provides a sort of encapsulation, we call a struct called a batcher, which does the bookkeeping for you and like does like a lot of work and a lot of testing and a lot of like really painful code review, which my colleague Eric has really been instrumental helping with, to make sure that like errors that can happen at any one of these stages are actually appropriately surfaced, don't lead to deadlock, and yeah, and so I think like this is another sort of like a high-level package design philosophy, right? Which is that, again, when you're developing a tool, you're looking for an abstraction that is going to provide just the right amount of flexibility and surface just the right complexity to your users. They want the sort of irreducible, unavoidable complexity, right? But not so much complexity that it's annoying to use and that they're going to be tempted to kind of go off and do their own thing, right? Yeah, and that's good for your users, and it's also good for the developers and the maintainers, right? So it makes it even in principle possible to test all the possible error cases that could happen in this kind of system, right? If you have a restricted API where you have this like batcher thing, okay. Yeah, thanks, that's all.
Okay, awesome talk. Sorry you had to be the last person to talk at JuliaCon. But if anyone has any questions, I'd be happy to hand it off. Sure.
Hi, thank you for the talk. So I think somewhere in between you mentioned that the labels may not align with the time samples. Could you talk about that more, why that would occur?
Oh yeah, I mean it can happen just because like, you know, I don't know. This is more kind of question about the nature of the data that we're dealing with, right? So a lot of times these are things that, so for this case, it's not all that common because like, this gets a little more into the nitty gritty of like the specific type of data. But like sleep staging is typically done starting on like even 30 seconds or like whole seconds at least, right? So if you have like a integer sampling rate, that's less likely to happen. But there's a lot of software that people use to annotate other kinds of events that can occur during an EEG, where they just sort of like click anywhere, right? And then like the software exports it to some other format and we import it to our format. And somewhere in that meat grinder, you can very easily get into a situation where like, if the sample is, if the signal is sampled at 128 hertz, you might get something that starts at a kind of weird random millisecond, right? That doesn't actually, like an annotated event that starts at a weird random millisecond that doesn't actually line up with that. So yeah, that's sort of why you get to those situations. Yeah.
Any other questions? Yeah.
Thanks, Dave. Great talk. My question is, how do you know where to draw the line in the functionality you express to users and what to hide from them? And then also, how do you prevent sort of complexity creep over time as it kind of grows into its niche, its use case?
Yeah, and I'll answer the second one first, which is that I think actually this, like, I'm starting to have, I'm filled with regret about this whole batcher service thing, because it has become enormously complex and difficult to maintain. Even when I have to go in and like make a change, it's really, really hard, right? So I think the thing is like, you just sort of like, you take a guess and you give it a try, and like eventually you have to be prepared to just sort of like cut pieces off when they become too complex or difficult to maintain, right? Or like, yeah. And as to the first part of the question, like, you know it when you see it, I guess is the only thing I can say, right? I think it's really, it's one of these, it's a real judgment call. And I think it requires like, like, I always like to say that like most of software engineering is like actually like sort of human and social problems and not technical problems, right? Because it's like, you're trying to like do stuff with computers, with other people, right? The computer is the easy part, frankly, right? The other people are the hard part, right? And so it's like, I think it is a lot of like, you need to be empathetic towards your users and sort of understand what they're doing and like have a lot of like theory of mind for like where they are going to run into trouble and make mistakes. And a lot of that stuff you just learn over time, right? And like I think like one of the sort of like the life cycle of this package started off in a very much more constrained case on one machine learning effort. And then eventually it grew into sort of, we try to generalize it and use it more broadly. And as we were doing that's the sort of point where you start to, you start to think about where can we generalize this and where can't we? But it's like, yeah, I think it's something unfortunately you have to learn over time. So yeah.
I'm sorry, I'm going to have to cut us off. We do have a closing speaker or something going on. I don't know.
Something's happening.
Yeah, I think it starts now. Yeah, so we got to go. Sorry.
Thank you.
Thank you again. I'm not really sure what the plan was. Because you have to, scramble all over.
I don't know. They don't leave it. They don't leave it downtown. I think it's probably in the keynote room.
I'm checking that. Yeah, it is.
Hiring